Yes, what is the question?
I'm wondering, can you hear me right now?
Yes, I can.
Oh, okay. So the way that when you present the infinite number of like winding numbers, it naively reminds me of the instantons in non-abelian gauge theories. Are they somehow related, like the totally non-perturbative effects?
Not directly related in that way, although it's very interesting that around a little over 10 years ago, there was yet another. I mean, there have been a few examples of cluster structure connected to physics, and this earlier example involved BPS states in n equals 2 supersymmetric gauge theories, and so this infinity is there as well, in the sense that as you sort of take these states around, they cross various walls in the moduli space, and they can pick up charges, and they can pick up more and more charges as you wind them around more and more and more. Those are some sort of non-perturbative objects for which this structure is important. I should say there is another. I could have said this at the very start, that this picture of the mutation relations was seen right around the same time the mathematicians were talking about, at least at the level of the picture of the quiver. It's also related to Seiberg duality in n equals 1 supersymmetric gauge theories. So when you take two theories that are dual to each other, you do the same thing. The sort of matter content is, for the dual theory, is what you get from the original one by swapping all the arrows. And so there is some sense in which these rules about mutations and dualities are related to dualities in interesting ways, but not directly the sort of instantons. No.
I'm sorry, but then, for example, naively in the non-abelian gauge theory case, it breaks the B plus L, like a global symmetry. In this case, it doesn't break any global symmetries. It doesn't have such effects.
No, it has. I mean, it doesn't have that interpretation at all. It's not associated with any symmetries or any not. I mean, these are just, these winding sectors are just what seems that appears we don't want them from the perspective of the amplitudes. It looks like there are just many copies of the same variable. On the other hand, they're a crucial part of the story of the triangulation of surfaces. So as far as the physics is concerned, in the end, you know, we have this form that includes all of them, and in the end, we can set them all to be equal. We can take an average. We can do all sorts of things. But as far as literally the actual physics is concerned, we want to think of all these variables as being the same somehow. It's just that we can't literally set them equal to each other. That would ruin everything. So somehow that's the challenge here, is that we have to find a way to include all these copies. We can't just stupidly make them literally equal to each other. That doesn't work. We really have to find a way to intelligently close the space, and that's what we've been trying to do. But as far as the physics goes, each one of these winding things, they're all just the same loop. We don't see the winding as far as the physics is concerned.
Sorry, just a final naive question.
So you can think about it as like yet another extension. You see, like in order, for example, to see this hidden symmetry and the projective invariance and all that stuff, we have to upgrade the amplitudes from just functions to forms. Once we upgraded the forms, we saw they had all this extra structure that we did not see when we just thought of them as functions. Now this is like kind of uplifting it one more. In order to see the structure and how everything is tied to each other and the whole thing, we actually have to allow what appears to naively be the same loop variables to have this winding index. And that's the beginning, but somehow it has to stop, it has to close. And that was the challenge, and at least in this class of examples, I think we have a way to deal with that challenge.
So hold on, if you couple that with fermions, can this change the picture? Like
well, we don't. I mean, so far we're not talking about fermions. I mean, you're sort of imagining this like something like
Singer theorem.
Well, yeah, no, we don't have anything like chirality, fermions, anything. I mean, we're talking about just amplitudes for the apparently very dull and boring scalar field theory here. So the surprise is that this apparently very dull theory has a lot of structure.
And sorry, just another naive question. So the fact that delta split the spacetime into two parts naively reminds me of the Casimir effect, in which we have a wall that divided the space and then has it has an IR singularity that has observable effect. Can that somehow have the same physical impact? Sorry, I'm just trying to understand the physics. Sorry.
Yeah, I don't think so. I don't see any direct analogy. In fact, it's not. I mean, what's sort of unusual is that this is to the extent that there is some kind of. I mean, it's maybe this delta is a little bit more like a wormhole. Like you have one part of a space-time, you have another part of the space-time. They're naively not allowed to talk to each other, but there's also a wormhole in the middle. This delta allows you to sneak from one to the other. Without it, you can't do it. But with the wormhole, you can sneak from one side to the other. If I wanted to make an analogy, that would be the sort of best analogy I could make.
Thank you.
But there really is something like a space-time on one side, something like a space-time on the other. They naively can't talk to each other, but delta allows them to talk to each other. And you can actually pass from one to the other. Where the word pass here means that we're allowed to write relations between the variables on one side and the variables on the other. Are there any other questions? Yeah.
Yeah, I have a question regarding the winding. So
Yeah.
so you gave an example where you had two punchers,
Yes.
two loop, and then the winding understood. But what about if there is only single puncture?
If there's only single puncture, there's nothing going on. And that's why the single puncture case was the case of the DN cluster algebra, and that was one of the finite type cases that is in our pocket already.
So it means the one loop does not lead to infinite.
No, the one loop does not lead to any infinite things because we don't have any, it doesn't mean anything to wind around. I mean, you might think, can I have this? But this doesn't mean anything because you can just unwrap this so that it just looks like that. Okay, so there's no winding here. So the winding really begins at two loops.
Mm-hmm.
And where things get really, really exciting is starting at three loops. Because starting at three loops, see what's really going on is that the winding is actually acted on by the braid group. I have three holes, and I can now remember there's an idea of the mapping class group. So I can take these punctures out and rotate them around each other any way I want and glue them back in. And so really, this is acted on by the braid group. Now the braid group for two punctures is just abelian, just winding. For three, we can have all kinds of crazy things, right? You can go around like this and do all kinds of stuff. Okay, so you have to start understanding. So all this pictures of the space-time and walking and all the rest of it starts acquiring this more interesting kind of non-abelian character to it. So yeah, I'll have a little bit to say about that in my Zoomplitudes talk. So when you go to three loops and above, and actually when you go beyond the planar limit, the kind of space-times that you run into start having a more cosmological character to them, by which I mean they grow. They grow with time as you evolve. So far, we've just seen static space-times. We've seen static space-times and you evolve, and then, okay. In the finite type case, you evolve and you're done. In these new cases, you evolve for a while, you stop, and then there's this sort of wormhole that lets you connect to the other side. But three loops and above, and also beyond the planar limit, you start seeing really new things, that the evolution in space-time actually grows, the space grows, you get more and more variables, the space actually grows. But there still appears to be some structure to it, and that's what we're in the middle of exploring. We're in the middle of exploring all these things now.
Another question, can we think of the notion of effective vertex, say if we have a one loop and we just...
Sure. Absolutely. In fact, that's an easy way to see subalgebras of the cluster algebra, if you like. Like, you can imagine putting some effective loop around all these guys. Actually, the easiest thing to do is to imagine actually tying them to each other. And then everything else that you do would sort of treat these guys as if they were, sorry, I'm drawing such a messy thing, but as if they're just an annulus there with two points. So very much so, that they're effective vertices, you can treat things together. And that's a way of seeing subalgebras inside the bigger surface cluster algebra.
Okay, thanks.
All right, shall we proceed? Okay. All right. So the last topic, I'll try to make this lighter, a little bit lighter, and not go on so long. Actually, this is something that a number of people are going to talk about at Zoomplitudes. So what I'm going to do is just give an introduction to sort of one aspect of it, which might not be, I don't know, it might be, but might not be highlighted in the talks, and I think the most elementary part of way of thinking about it, but which I think is quite beautiful. So I just want to say a little bit about it, maybe to give context for people who want to get something out of the corresponding talks at Zoomplitudes, as I said. So here we're talking about, we're switching gears and going all the way back to n equals 4 super Yang-Mills. And let me repeat some of the things that I said in the morning. So in n equals 4 super Yang-Mills, we have a very simple picture of the kinematic space. Okay. And if you know what these things are, well, probably by now most of the people online know what they are. But if not, you can just take it on faith, and it's very easy to think about anyway. The kinematical space is just a set of n momentum twistor variables. Okay, so these are 4 vectors, and there's an ordering to them, so they are ordered. And furthermore, the information about helicity is encoded under what we think of as the little group transformation. What happens when ZA goes to TA ZA? And different components of the amplitude or of the super amplitude have different weights under this transformation. Okay, so so that's the space. The dual conformal symmetry acts on all the z's by 4x4 linear transformations. So that's this SL4 symmetry. I can just loosely think of it as a GL4 because I have the overall rescaling as part of the little group transformation anyway. And so anyway, that's our kinematical space. You see the sort of big difference between this kinematical space and the one that we've talked about all the time for the bi-adjoint theory is that the bi-adjoint theory is about these Mandelstam invariants, so it's dot products. It has to do with pairs of variables. And so that's where the sort of the two-dimensional space-time, all the two-ness of the story has to do with the fact that the kinematical variables we're using involve pairs. That's not the case here for n equals 4 super Yang-Mills. The variables are literally the variables associated with each particle. Okay, and so, but again, we have the same question. We want to ask a question in the space of n 4 vectors, a question in the space of n 4 vectors, whose answer is the whole amplitude. And really, ideally, we want the answer is the whole non-perturbative amplitude. I mean, if we're really dreaming, we might as well dream, right? Now, there is a kind of a picture for what such a question might look like, not for the whole amplitude, but for the integrand. So if we talk about the amplitudes at loop level, at tree level, for example, even or when we have loops, we don't imagine doing the integrations. We keep the loop variables as part of the kinematical variables. I won't describe the way this works in the detail, but anyway, but here's the gist of what's going on. In fact, I'll describe the gist of what's going on at tree level, which has and this is the story of the amplitahedron in kinematical space. Okay, which is in the momentum twister space. And the idea is sort of very much like what we saw in the bi-adjoint case. In fact, it was seen here in the context of the amplitahedron. So it's a much fancier setting. It was it was where the fact that it's possible to see these things in kinematical space was sort of seen first, again, in quite a bit more, ironically, in quite a bit more sophisticated setting. But anyway, here's the rough picture, is that in the space of Z's, there is a positive winding part. In other words, if I take the configuration of all these n four-dimensional vectors, there are some configurations that have some positivity and some topological properties. Now, I'm not going to tell you what these are in detail, but I'll give you an analogy, which actually, so there's a version of this story, not just for m, but for vectors, but for m vectors. Okay, so if you have m by n vectors, then here's what we mean by this subspace. So imagine I have two vectors. So I'm just going to plot the two vectors. So here's the two vectors, z1, z2, z3, whatever they might look like. So I'm just going to plot them. Let me just draw the sort of tips where the actual points are. Okay, so if I draw where all the actual points are, then the claim is that what the picture's got to look like, the sort of positive winding space, what we call GW of m in this case equals 2 and n. Okay, so this part of the space just looks like this, for instance. Okay, so here would have to be like 1, 2, 3. These are literally two-dimensional vectors, so two-dimensional points. Here's the origin, 5, 6, 7, 8, 9. And you see the sort of important thing here is, first of all, as you go from point to point, everything is winding in the same direction. Okay, so everything is winding in the same direction. 6, 7, 8, 9, 10. The fact that they're all winding in the same direction is actually a statement of positivity. That if I call these vectors Zi, it says if I take the determinant of Zi and Zi plus 1, they all have to be positive. So that's one condition. And so that's what it means to be positive. Then there's this winding, and the winding means that the path has to have winding number W. So you see, this is a part, and not a random configuration of the Zs will not look like this. Like, here's a random configuration of Zs, some totally crap configuration of Zs. This fails everything. Okay, if this is Z1, Z2, Z3, Z4, Z5, you see, they're not even winding around. They're not even winding around the same way all the time. Okay, so it fails that. So there's a special configuration of Zs that has this property that it winds uniformly. It winds uniformly, and it has some specified winding number. Okay, so that configuration, this is just a name for it, but it tells you in the space of Zs, there's a region, there's an interesting region, which is positive in the sense of a uniform direction of winding, and it has winding number W. And it turns out, so this is that here I could draw a picture, but there's actually a generalization of this. In general, instead of the winding number, there's a more convenient index K, which, if you know about n equals 4 super n mils, is the K of n to the KMHV amplitudes. But there's a space that's, for any m, it has this exactly the same character. It's positive in the sense of a uniform, now a higher dimensional notion of winding, which I could be more explicit about, but I'm just trying to give you a flavor. And K specifies the winding number. So this kind of has a different character. In the space of Zs, I just have a bunch, again, here's our problem. I have the space of n 4 vectors, n vectors. What the heck can I do in the space of n vectors? Well, once again, I have this notion of ordering. That's a big one. I have a notion of ordering. It lets me talk about who comes after who. And then once I have who comes after who, I can start drawing these topological pictures. But they have to wind this way, they have to wind around, and that starts putting some structure in this space. Okay, so in the story of n equals 4 super Yang Mills, that's an interesting part of the momentum twister space. That's an interesting part of this configuration space, of this kinematic space. And then the rest of the story is very similar. So that's the space, and you have to find a family of subspaces, just like we saw in the story of the isosahedron. There, in the isosahedron, everything was really simple. The positive space was just saying that all the x's are positive. That's it. The subspace was given by solutions of the wave equation. And the intersection of the subspace with the demanding that all the variables are positive revealed the isosahedron. Similarly here, we begin with this positive winding space. Now this is a fancier thing that lives in this kinematic configuration space. We again intersect it with a family of generalized hyperplanes in this space. And now the intersection of that hyperplane and this positive winding part is the amplituhedron. And the amplitude is the scattering form with logarithmic singularities, again, that's defined everywhere for all z's. But when you specialize to the, pull back to this subspace, it has to be the form of logarithmic singularities on the boundaries of the amplituhedron. The reason I'm telling you all of this is so you see that we really are thinking about these as n four-dimensional vectors, and the final object we get is a 4 times k form, or an m times k form, and k is the information about helicity. K tells you how many negative helicity gluons you have in the amplitude. K is so k has some importance in this story, right? But let's specialize for a second to the case of k equals 0. Okay, so if I now go back, if I specialize the case of k equals 0, then it turns out that this sector with winding number equals 0, essentially. So now we're talking in the language of n equals 4 super Yang Mills of MHV amplitudes. So they don't have any of this interesting helicity dependence. That's all sort of stripped off. And MHV amplitudes, famously, the actual amplitudes, well, they're just functions of ratios. They're functions of conformally invariant ratios, cross ratios. They don't have any helicity dependence at all. And at the same time, the space that we're talking about just turns out to be the winding number equals 0 space of 4nn, is just this famous positive Grassmannian, G plus 4n. In general, the winding number space is not the same as the positive Grassmannian, but in the simplest case where the winding number is 0, it is the same as the positive Grassmannian. What is the positive Grassmannian? Well, it has a very simple definition. It's for general, in this case, let's say for 4 and n, the positive Grassmannian is just a 4 by n matrix. So let's just write it as Z1 through Zn, the way we have been. But with the important property that all of the minors are positive. So if I take any 4 columns, so long as the columns are in increasing order, I have to give them some order because the determinants are antisymmetric. But if they're in increasing order, all of these determinants, all these minors are greater than or equal to a 0. Okay, so that is a very beautiful space. There's a lot that's understood about it, and it's played a big role in many aspects of thinking about amplitudes. Okay, but remember I told you this is all of this business about the winding, even when we specialize to 0 and so on, is about the integrand. And the actual amplitude are not just functions of these 4 vectors. The actual amplitudes are invariant, literally invariant. These MHV amplitudes are literally invariant under ZA goes to TA ZA. In other words, this overall scaling, which plays an important role in telling you about the helicities, so we can't ignore it. We can't really say that the Zs live in projective space because the overall scaling of the Zs really matters. But for MHV amplitudes, at least, and presumably beyond, but we can start focusing on the simplest case, this is literally irrelevant, and the actual amplitudes are invariant under z goes to tz. So in other words, we have an interesting thing here, that whereas at the side of the integrand, what matters is g for n, let's say g plus 4n for the external data. For the actual amplitude, what matters is g for n, except we have to mod out by the rescaling of the ZA's goes to TA ZA. And often we say that this is g for n mod torus, where this torus means just this rescaling of ZA goes to TA ZA, right? So that's something we'd like to understand. We understand a lot about G4N. We would like to understand what we could even mean by G4N mod torus, how to think about it, what's going on here. And clearly this is somehow connected this is also connected to the cluster algebra structure. They're both connected to the cluster algebra structure of G4N, although in this discussion, I'll say very little about the cluster structure. That will be discussed in the talks at the Zoomplitudes. Really what I want to do is give you a picture for what G4N or GKN in general, mod torus, looks like, how to think about it. So now, why do we care about this? We care about this because for the story of the integrand, it was a very important first step to figure out what the actual geometry is that matters for the integrand. Okay, so if it's positive moving space, and we discover the intersection of this positive Poynting space with the plane, and that's where the amplitude comes from. That's where the amplitude comes in. The amplitude is then a slave to that geometry. Once you figure out what the geometry is, then there's a natural question you ask of that geometry, and the answer is the integrand for the amplitude to all loop order. We would love to find the analog of that question for the whole amplitude, and it seems like at least one first step is to try to figure out what the geometry should be, what the analog of the amplitude should be for the actual amplitude rather than for the integrand. And already here is the first step in this direction is to figure out how to go from G4N, which is relevant to the integrand, to G4N mod torus, which is clearly the thing that's relevant for the amplitude. Okay, so that's the thing that we want to understand. All right. Now, before getting to something hard like or something harder like G4N mod torus, let me begin by talking about G2N and G2N mod torus. And I can do this without assuming that you really know anything about the positive Grassmannian. In fact, we'll see everything we need as we go. So what is G2N? Sorry, the positive Grassmannian. Well, it's a space of 2 by n matrices where all of these minors are positive. Okay. So let me just think about what those would look like as two-dimensional vectors. It looks like something like this. Looks like some two-dimensional vectors. Since saying that all the minors are positive says that it looks like that. Okay. So it means that 2 is forward from 1, 3 is forward from 1, 3 is forward from 2, and so on. So what would not be legal is, for example, 4 was there. That would not be legal. But everyone is on the same side, and everyone is ordered in this way. So if you give me a bunch of 2 vectors and you ask for all of the minors to be positive, this is what the configuration of 2 vectors actually looks like. And so you can ask, what do the boundaries of the positive G2, for example, 4 look like? And so it's clear that what the boundaries look like. For instance, I should make this vector parallel to that vector. If I make it parallel to that vector, then I'd have 1 and 2 on top of each other in the same direction, and 3 and 4 generic. Or the other way, I could have 1, 2, and 3 on top of each other, 4 generic, and so on. Okay, or I could have 1, 2, 3, and 4 on top of each other. And we can also see this algebraically at the level of the matrix. So you can always do a 2 by 2 linear transformation to bring any 2 of the vectors to this form. Let's say 1, 0, and 0, 1, just basis vector. So let's say the other ones look like x, y, negative w, z. And you can easily see that all the minors, like the minor 1, 2 is equal to y. The minor 2, 3 is equal to x. The minor 3, 4 is equal to w. The minor 1, 4 is equal to z. And so if I just say x, y, z, and w are positive, all the minors are positive. In fact, the only one that's interesting is 2, 4, which is xz plus yw, which is indeed positive. Okay, so this is what a generic part of the positive G24 looks like. And again, you can see that to go to the boundary, I would want to say, let's say x to 0. If I send x to 0, then I get 1, 0, 0, y, 0, 1, negative wz. So what's happened is I've made, if I set x to 0, I've made the column 2 parallel to the column 3. Okay, and so on. You can see that if you send any one to 0, that what's going on is that you're just making two of these vectors lie on top of each other. Okay, so very simple. That's the picture of the positive Grassmannian. Now let's go back and think about what the positive Grassmannian mod torus looks like. So what does mod torus mean? It just means let me draw a generic point in G24 again. Mod torus means that I don't care about the sort of overall length of these vectors. I just care about the whole ray. It's like in projective space. Okay, so I just care about this whole ray. And as usual, I can sort of think about what some representative is by intersecting this with some line. So if I look on that line, I would just have 1, 2, and 3, and 4, like that. Or as usual, if you're used to these things in complex analysis, we can also imagine mapping this to the boundary of a disk. So we'd have 1, and 2, and 3, and 4. It's all the same. So if I do a count of dimensionality, what is the dimensionality of the positive Grassmannian G24? Well, it's 4-dimensional. We just saw it, right? That was our parameterization, 1, 0, x, y, 0, 1, negative wz. But the positive Grassmannian mod torus is only 1-dimensional. Okay, and we can see that it's only 1-dimensional because I get to rescale all of these columns, and so that naively that takes me down 4. But remember, up here I'm identifying in G24. I'm identifying anything that differs by general GL2 transformations, not just SL2 transformations. So anyway, the dimensionalities are the dimensionality goes down by 3. In this way. Now, super naively, you might think when you mod up by torus, you make the object simpler. I don't know, it's lower dimensionality. You make it simpler. By the way, what's the story in general for G2n? Well, it's 2 by n matrices, so there's 2n degrees of freedom, but it's minus GL2, the GL2 transformations. So it's 2n minus 4. So that's the dimensionality. Sorry, the dimensionality of the Grassmannian, not just the positive Grassmannian, but the dimensionality is 2n minus 4, whereas the dimensionality of G2n modulo this rescaling of the columns is n minus 3. You'll notice this is the same as the dimensionality of all the polytopes we were talking about. Okay, so this is in our story of the icosahedron and so on. Okay, so that's not a coincidence. Okay, but let's try to get an idea. And this is again very standard if you've done this in string theory or elsewhere in elementary math. Let's try to see what some nice coordinates look like for. So let me begin, for example, with these coordinates. Let me write it like this: x, y, z, w. Okay. So those are some generic coordinates for G2n. Again, but for G24, let's say, I use the freedom to put the first column and the last column to 1, 0, and 0, 1. So that's G24. But now what I'm going to do is use my freedom to rescale columns. Okay, so if I use my freedom to rescale columns, I can always scale the top components here to be 1. All right, that seems to leave me with 2 degrees of freedom. But now I can do something else. I can do a GL1. In other words, I can do a rescaling just of the bottom row. Let me do a rescaling of the bottom row, for example, to multiply it by this 2 by 2 matrix, 1, 0, 0, 1 over W. So that's the same as just rescaling the bottom row by 1 over W. And what I get is 1, 0, 1, some Y over W that I'll call the final variable Z, 1, 1, 1, 0, 1 over W. So now I have a 1 over W stuck at the bottom here, but I can also rescale this last column. Okay, I can also rescale this last column by W, and that takes me in the end to 1, 0, 1, Z, 1, 1, 0, 1. Now, this presentation is the one that you're often used to. Okay, like when you say 1, 0, 1, Z, 1, 1, 0, 1, if I think about these as points in projective space, I would just look at the bottom component. And so this is the origin. So this is saying you have an origin. This is saying something at point Z. This is saying you have something at 1. And this is the point at infinity. And so that's what we normally do when we talk about points in projective space. Okay, so that's what the sort of typical interior points of GKN and of G2N and G2N mod torus look like.
Can I bother you with a question?
Sure.
Yeah, so in the plot that you presented, in which you had the 4 G vectors, and then you just replaced that with, like, you relaxed the rescaling. So it naively seems to me that the degrees of freedom are actually 2 angles that define, like, the angle between 2, like, G vectors inside the first and the last column, and then an angle between the first column and second column.
No, we don't have any.
What I'm getting wrong?
No, we don't have any angles here. One thing that you have to realize is that we don't have a metric here. We're allowing ourselves arbitrary linear transformations, not just rotation. It's really arbitrary linear transformations. So, for example, these 2 vectors and these 2 vectors, and all of these things can be just related to each other by linear transformations. The angle is not invariant. There's no notion of angle. The notion of angle is needs a metric. We don't have that. Notion here. We don't have lengths or angles. So we're just allowing ourselves random, arbitrary 2 by 2 linear transformations.
Oh, thank you. Now I see.
Yeah. So, and actually, the sort of manipulation that we just did is just the way to explicitly see that the space is one-dimensional. So again, naively, you might think that we have G plus 2n, and remember, in G plus 2n, we also have this ordering, which after we turned it into the rays, meant that the points were ordered on this line. Okay, so in all the cases both cases we have 4 ordered points. So here's like 1, 2, 3, 4, or if we draw it in this disk, it's like 1, 2, 3, 4, like that. Okay? So you might naively think that G24 is more complicated than G24 mod torus. But actually, in many ways, G24 mod torus has a more intricate and interesting boundary structure than G24 itself does, or at least a quite different one. For example, we already saw in G24 that the boundaries can look like just columns 1 and 2 become parallel to each other, or just columns 3 and 4 becoming parallel to each other. And these are separate boundaries. Okay, so this is a separate boundary than this one. One parallel to 2 is one boundary. 3 parallel to 4 is another boundary. You see, the structure of the positive Riemannian itself is very local. You only care about what happens when vectors become near each other, or when nearby vectors end up being parallel to each other, and then sort of generalizations of that as you go down. But the structure of the boundary of G2N mod torus is more interesting than that and is more global. And I just want to describe how this works. So this is really the most basic aspect of this kind of story, but I want to say it in this language so you have an idea of what we're going to be looking for when we go to the higher cases. So so let's see how this works. So for instance, you might very naively think. So let's say that we do the same thing. Now I'm going to do something like this. So I'm going to go to this. I'm going to go to this presentation. Okay. So let's say before doing all the rest of the rescalings, just so I'm going to make my life a little bit easier. Let's say I start with this x, z, w, y, w, 0, 1, and I'm just going to rescale the top components to all be 1. And the last one is still 0. So 0, y, w, 1. Okay. So okay, so I'm still just talking about G24. If you like, I'm just I'm choosing to have vectors where the top components are all positive and just rescaling them to be 1. Now, so there's a sort of there's an obvious boundary where y goes to 0. In that boundary, naively, column 1 is becoming parallel to column 2. Okay, good. So that seems to be the boundary. That's just what we expected. These two vectors are parallel and these ones are not. But let's see what happens if we actually try to do that, not just in G2N. So this is in G24. But let's say what happens if we do this, if we try to do this in G24 mod torus. So let's say I put y to epsilon to remind myself that it's tiny. Okay, so there it is. But you see, no matter how tiny I make epsilon, there's always a GL1 that I can do here that takes us out to 1, 0, 1, 1. I'm going to multiply by 1 over epsilon. Okay, and then I have 1 W over epsilon and 0, 1 over epsilon. I will still rescale this column so that goes back to 0, 1. And then I'll rescale this column to put this W, and then this will be epsilon. So you see, no matter how tiny epsilon is, there's another component of the space. There's another component of the space where the two columns are not close to each other at all. Instead, what's happening is that as epsilon goes to 0, it's column 3 that's becoming parallel to column 4. Right? As epsilon goes to 0, column 3 becomes parallel to column 4. So that's somewhat remarkable that the boundaries of G24 are simpler than the boundary of G24 mod torus. In fact, the boundary of G24 mod torus is a one-dimensional space. The boundary of G24, or this positive G24 mod torus, looks like this famous picture that I discussed earlier in the very first lecture today. It's that we can either think about it as 1 and 2 on top of each, separate, and 3 and 4 on top of each other. That's sort of one component of the boundary. Or there's another component of the boundary where we can think of it as 3 and 4. Apart from each other, and 1 and 2 smushed on top of each other. So, in other words, we can think about this in the following way: that how are we approaching this boundary? You know, I'm taking 1 and 2, I'm bringing them closer and closer to each other. Here's 3 and 4, and from the perspective of 3 and 4, they see that 1 and 2 are just getting closer and closer. No problem. In the end, 1 and 2 just hit each other. So from the perspective of 3 and 4, the end result is that 3 is here, 4 is there, and 1 and 2 are on top of each other there somewhere. But from the perspective of 1 and 2, we can always do an SL2 transformation. That's just what we did. We can always do a transformation from the perspective of 1 and 2, where 1 and 2 are apart from each other, and exactly what we just saw. The transformation that we did to put 1 and 2 apart smushes 3 and 4 on top of each other. Okay, so from the perspective of 1 and 2, 3 and 4 are on top of each other. And so we get this much more interesting picture, again, drawing again, this bubbling picture, where on one side we have 1 and 2, and on the other side we have 3 and 4. Okay, so I'm as I said, I just want to say some elementary things here, and just now give you a picture of what things look like in the higher cases. And this is really an invitation for you to pay attention to the lectures on this topic. There's a few lectures on it, a few talks on it at the meeting next week. But so what's the story in general? For example, just to stress again how much more intricate it gets, for G2n, for positive G2n, just in general, the kind of first boundaries, now I have a bunch of vectors, not just 4 of them, but once again, the kind of first boundaries that we talk about, the codimension 1 boundaries that we talk about, the codimension 1 boundaries are just when column I and becomes parallel to column I plus 1. That's it. Pretty boring. But for G2n mod torus, this bubbling picture looks like factorization. Okay, you can have a bunch of guys smushed together on one side, and another set smushed together on the other side. And it's the same thing. It's like from the perspective of these guys, it looks like all the rest of 1, 2 up to J are smushed on top of each other, and similarly from the perspective of the other one. So you see in this very simple example, this sort of more global aspect of the boundary structure of the moduli space for G2n mod torus compared to that for G2n. G2n only cares about 2 columns next to each other, whereas G2n mod torus cares about the whole thing. It has to split in 2 in this more interesting way. Okay, so that's the kind of challenge to figure out what the analog of this is and what the analog of this bubbling picture is for higher K. And so I'm not going to describe systematically how it works. I'll leave that for the fun of lectures, but I just want to show you a picture again to give you a flavor of what this thing actually looks like. Let me show you a picture of what it looks like for G3n. Not G4n, but I'm going to show you a picture of what things look like now, both for positive G3n as well as positive G3n mod torus. And in fact, here I'll just restrict to n equals 6. Again, it's a lot richer, so I'll give you some flavor for that richness. But let's first think about what positive G3n looks like. Now, this is also something we can visualize pretty easily. These are 3 by n matrices where all the minors are positive. So we'd say all the minors, CA1, CA2, CA3, that they're all positive if A1 is less than A2 is less than A3. Now, let me give you an easy way of visualizing this. Let's imagine that we rescale the top column to all be 1. You can actually show that it's always possible to do that. So let's say that I rescaled at the top of all of these 3 by n vectors to be 1, and the bottom I'll just call x1, x2, up to xn. Right? So this is what my 3 by n matrix looks like. This is even a good preparation for modeling by torus anyway, where we might want to rescale the top component. We might want to rescale the top component to be 1. Now, what does it mean for the minors of this matrix CA1, CA2, CA3 to be positive? Well, what are the minors? The minors you'll recognize as your high school, like the minor 1, 2, 3. This you'll recognize as your junior high school formula for the area of the triangle. If I put a half, the area of the triangle with vertices x1, x2, and x3. Okay, so that determinant formula is just the area of a triangle. And so you know what it means for this thing to be positive. It means that 1, 2, and 3 are oriented like this. They're oriented to go around like this rather than the other way. So what does it mean for all the minors to be positive? What does it mean if I plot these 2-dimensional vectors? Well, it means something extremely simple and pretty. It means that these vectors are just the vertices of a convex polygon. So here is x1, x2, x3. And so you see that for these to be, all the minors to be positive, it just means that the x's can't be random, but they have to be the vertices of a convex polygon. So that's a very nice way of visualizing G3n. You can think about, generic configuration as just being the vertices of an n-gon in the plane. And you can also see why there's so much richness to the structure, to the boundary structure, because you might naively think that to go to the boundary, I can take any old 3x3 minor and set it to 0, but I can't do that. Because, for example, if I want to set the minor 135 to 0, setting the minor 135 to 0 means that the point 1 would have to lie on the line 3, 5. 1, 3, and 5 would have to be collinear. So let's say I try to do that. Let's say I take point 1 and I try to move it towards the line 3, 5. You see, I can't get there. Before that happens, 1 will end up on this edge 2, 6. So I can't keep going while preserving the convexity of the shape. So you can see that the boundary structure, now this is for k equals 3, the boundary structure now involves, once again, nearest neighbors. Like I can go from this picture to one where these guys are collinear, okay? And then let's say after this, if I wanted to go to one lower boundary, I could, for example, make this point live on top of that point, or I could maybe make these guys collinear, and so on. But there's a fairly rich boundary structure to the Grassmannian, for the positive Grassmannian, and it's a very beautiful and deep and rich story for what the boundary structure looks like. But what I want you to see is that it still involves local information. It involves something about the linear dependence between k nearby guys. For the Grassmannian of G2n, it involves things between 2 neighboring columns. Here it involves whether 3 neighboring points in this polygon are collinear or not. And generalizations of that as you go down to lower dimensionality, okay? Lower dimension boundaries of the positive Grassmannian, okay? So, but it's still local. It's just like in the G2n picture. So what I now just want to do is tell you at least one picture for what G36 mod torus looks like. And if we had longer, I would tell you that that it's actually not God-given what we mean by these by G36 mod torus. We're actually making we're making choices about how to sort of complete the space or compactify or compactify the space. What I'm telling you is a particularly natural and beautiful way of doing it. And this natural and beautiful way is actually related to a number of other things that will be talked about at the Zoomplitudes meeting. It's related to something called the positive tropical Grassmannian that Lauren Williams and David Spire talked about many years ago. It's related to some beautiful recent work of Nick Early and Freddie Cacciazzo and other people, and Lauren and Tomek Lukowski and Matteo Parisi. So there's a lot of really fascinating things going on in this general subject. But what I don't want to tell you about all of that. You will hear about that at Zoomplitudes. I want you to give you a sense for what this space actually looks like. What is the analog of this bubbling picture? What actually happens if you go to the boundary of G36 mod torus? And at least in this nice way of thinking about what it is. And so that's what I'm going to end with here. It's just a picture of what G36 mod torus looks like. And then I'll tell you a few words about how this ends up being related in sort of surprising ways to some of the other things that we've been talking about. Polytopes, stringy canonical forms, and so on. Okay, so what does G36 mod torus look like? Now, let's try to guess a few things. Okay, so for example, you might think that we know that in G36 itself, we already talked about the fact. Oh, so that's too many. We already talked about the fact that we have a boundary where 1, 2, and 3 can be collinear with each other. For example, 1, 2, 3, 4, 5, 6. Okay, so 1, 2, and 3 can be collinear. So let's just imagine in our mind, this is just like in the G24 example. Let's imagine in our mind that we are getting really close to that but not quite there yet. We're getting really close to these three being collinear. I drew it the same way. Okay, really close to being collinear. But now what we're allowed to do in G36 mod torus is the same thing that we did before. We say, even though they're getting really close, no matter how close they get, I can always do an SL3 transformation that undoes it and puts them back in generic position, 1, 2, and 3. But what do you think that transformation is going to do to 4, 5, and 6? It's going to squash 4, 5, 6 on top of each other. Okay? Oops. So there is at least one component of the space that's sort of familiar, and it looks like the bubbling picture. In other words, one component looks like 1, 2, and 3 on top of each other, and 4, 5, and 6 generic. But another component, again, from the perspective of the 1, 2, 3 world, there's 1, 2, and 3 generic, but 4, 5, and 6 squashed on top of each other. Okay, so this is sort of one of the boundaries of G36 mod torus. So this is the sort of most obvious analog of the bubbling picture. Here's another component. This one's a little more interesting. You can imagine that you take 1 and 2 and you put 1 and 2 on top of each other. Now that, from the perspective of G36, is an even lower dimension boundary. I can get to putting 2 points on top of each other only after I do a lot of other things, but let me just do that here. So let me imagine that I'm putting 1 and 2 right on top of each other. So here's 1, 2 right on top of each other, and here's 3, 4, 5, and 6 generic. Okay, so that's one component of the boundary. But once again, exactly the same story. What I can do on the way there is undo that transformation, put 1 and 2 back to being generic. So what do you think that's going to do to 3, 4, 5, 6? It's going to squash 3, 4, 5, 6 on the line. Oops. So this is another component. But the most interesting component is the following one. And I'll just tell you what the answer is. I encourage you to do the exercise just like we did in G10, to do it here, to really imagine going to the boundaries that we're talking about by taking a 3x6 matrix, making a parameter small, and just by hand doing it to see that you can undo the transformation and make what I'm about to show you happen. What's interesting about this is, as we'll see, this no longer bubbles into 2 pieces, but it actually has 3 pieces, okay? And it looks like this. You see, it'll be quite a bit more intricate. We can have 1 and 2 on top of each other on a line with 3 and 4, with 5 and 6 generic, or we can just cycle all the indices up by 2. We can have 3 and 4 on top of each other with 5 and 6 on a line and 1 and 2, or we can have 5 and 6 on top of each other with 1 and 2 on a line and 3 and 4 generic. So this is a 3-component bubbling, quote unquote bubbling. Okay. And I really encourage you, if you've never thought about these things, I would encourage you to, as I said, really try to work through this example and see how it actually works. This already shows how much richer it is. This is a codimension 1 boundary. Okay, so really in G36 mod torus, there's a 1 parameter family of sort of curves that you can take in this space that in the extreme limit of the parameter hits this sort of funny configuration. And there's actually sort of 3 different configurations that you can land on. Again, this is the analog of the 2 worlds in the G24 picture, where from the perspective of any one guy, the other guys are squashed on top of each other. Well, this is now splitting into 3. And it's really interesting and fun to work out how this works. And actually, there's a final component. There's a final kind of boundary that looks exactly the same, but where it's another 3-component boundary where it looks like this: 1 and 2 on top of each other, and then 3 and 4 at the end of this line, with 5 and 6 together with the cycle by 2. Okay. All right. So there it is. We have there it is. We have a there's an interesting notion of what we mean by GKN mod torus for any KNN. I've shown you examples of what it looks like for G36. And now let me say a few general remarks. And again, this is really mostly a setup for some of the things that will be talked about.
Excuse me, Nima.
Yes.
Just curious if you'd like to comment on the question of whether these 3 and higher component boundaries suggest any type of field theory where factorization is not into a product of 2 lower things, but 3 or more lower things.
Yes, indeed. I mean, that's that's just where I was about to.
Oh, okay.
Yeah, that was one of the comments I was about to make. But in fact, I wanted to go back and contrast the story with the G2N again, right? So for G2N, let me just remind the analog. In fact, let me draw it sort of one dimensional so it's kind of clear. So we just have these points, and the bubbling picture tells us that it's kind of the direct product of 2 things like this. Okay. So that's already pretty interesting. We sort of draw it more conventionally like this, of course, as we've talked about already. But here we also know, in this case, we also know, and we've talked about at length earlier in these lectures, we know that the collection of all of these objects, in other words, all the boundaries of G2N mod torus, they factorize into lower guys. We know that these are captured by a polytope. We know they're captured by the icosahedron. What is that polytope? It's a polytope whose facets are the first factorizations, and then I keep going. The edges are continuing to bubble, and I keep going down until I get to the vertices, which are the complete bubblings where I can't go any further. Okay. Already for G36 mod torus, we see there is something similar. We solve some, there is a notion of G36 mod torus. We can ask whether there is some kind of geometric object, or there's a polytope that captures all of the combinatorics of its quote unquote factorization. And as Mark said, now it's whatever it is, it has to involve things that factor into the product of 3 pieces or even more pieces as we go to a higher end, even in G3N mod torus. Okay? Now, quite beautifully, the answer to this question is yes, there is a polytope. There is a polytope that captures all of this combinatorics of the factorizations, all the combinatorics of the boundary structure of GKN mod torus. And there's a variety of ways of describing what it is, but in the spirit of the lectures, I want to, and also in the spirit of showing all these strange connections between string amplitudes, n equals 4 supercritical mills, phi cubed by adjoint theory. Let me remind you one way that we could get, I don't think I actually said this explicitly before, so I'll say it now. One way to get the canonical form, so we want to find the sort of polytope. It turns out to be the icosahedron, right? We want to find this polytope that captures the boundary structure of G2N mod torus. And what captures that is the string amplitude. Okay, so what captures that is we take G2N mod torus, and we integrate. There's a form with logarithmic singularities on the boundary of G2n mod torus. I'm writing this notation. If you haven't seen it before, don't worry about it. But this is so these are the minors of the 2 by n matrix. I'm calling the variables sigma by convention. I could call them C because I'll call them C later. But so what I'm integrating over is 2 by n matrices, C1 up to Cn. So 2 by n. But then I have the product of all of the minors ij to the power of some alpha prime Sij. Okay? And I put the power of alpha prime to the n minus 3 out in front of the whole thing. Okay, so this integral is the stringy canonical form. Okay, in fact, this is the string amplitude. This is just literally the string amplitude, and it turns out that you can literally put it in the form of the stringy canonical form if you parametrize the minors of this matrix in an intelligent way in so-called positive variables. Anyway, it'll take a little long for me to describe what that is, but this is exactly the general story of the stringy canonical form. We have a space that we're integrating. This form turns out to have logarithmic singularities on the boundaries of the positive Grassmannian. And so naively, if I just did this integral, I would get something divergent. So I have to regulate by putting the powers of minus to various powers. These Sij's have to satisfy the constraint that looks like momentum conservation, the sum of I not equal to j of Sij equals 0, in order for the integral to be well defined. But once I do that, I have an object that now depends on these exponents, and we can run the whole story of stringy canonical forms on it, and we see that this object is associated with a polytope, and the polytope is exactly the isosahedron. Okay? So what I want to say is that on the one hand, we have a picture that we want to figure out what we mean by G2n mod torus. But on the other hand, once we write down these integrals, the integrals just tell us what we mean by G2n mod torus. When you write down this integral, the entire subtlety is how precisely to think about what happens when minors are going to 0. The sort of entire subtlety of figuring out what you mean by what you mean by the space is how to treat what happens when points collide. And this is kind of a very famous fact in the geometry, that what you mean by a space is not sort of purely a function of how you draw it. For example, if I draw this, if I draw the upper plane, I might just say I have x and y bigger than 0. And what do I think it is? Well, I just think it's the plane, and that's it. There's a vertex there, and that's it. But that's only if all I care about are simple polynomials in x and y. If I care about the ratio x over y, then that's not true anymore. Then in the neighborhood of this point, there is a whole line that lives here that knows about the ratio of x and y. So this is the entire subject of blow-ups when you think about singularities in geometry. And so when we say that we're talking about what we mean by G2n mod torus, implicitly we're making some declaration about what happens when points get near each other, what happens when they collide, and or when we go to the boundaries of GKN itself. Okay, so so there's some choice that's always being made there, but once we write these integrals, you see, the integrals tell us what choices to make. The integrals are perfectly finite, they're regulated, everything is fine, and the integral forces a choice on us. And it tells us the choice that it's forcing, precisely because as alpha prime goes to 0, the integral becomes the canonical form of a polytope. And the boundary structure of that polytope is precisely reflecting the compactification that we have, the way that we've compactified this, the choice we've made in compactifying the moduli space. So on the one hand, there's a very natural and beautiful, intrinsically geometric picture of thinking about what GKN mod torus looks like. It's associated with words like hypersimplex decompositions and so on. Some of it will be talked about at Zoomplitudes. So there is an intrinsic natural way of talking about it. On the other hand, there's also a way of defining it directly by thinking about the analog of these stringy canonical forms. And there is an analog of the stringy canonical forms, not just for G2n, but for any Kn. For a general GKN, there is an analog of this form with logarithmic singularities, and instead of being d2 times nc over all these minors is simply mod GL2 is simply dk nc mod GLK over the k by k minors, 1, 2k up to n1 k minus 1. And so we can define a stringy canonical form type integral as an integral over the positive Riemannian mod torus. Now this we have to mod by torus because this integral is actually torus invariant. If we didn't mod up by torus, we'd get a divergence. So this is mod torus. This is an integral over the positive Riemannian mod torus. And again, we multiply by all the minors, I1 through Ik, to some powers of Si1 up to Sik. And the resulting object is associated with a beautiful polytope. So as alpha prime goes to 0, we get from this integral the canonical form of a polytope. What you can call the like GKN mod T polytope. The polytope that captures the boundary structure of GKN mod T in the same way that the isosahedron captures the boundary structure of G2N mod T. Okay, and something that seems quite beautiful and is being explored, and it's not clear exactly what it means, but there's some evidence that there's something non-trivial and nice going on with it, is that if we specialize in the case of G4N mod T, and G4N mod T is the thing that we want, then we can associate the normal vectors. We can associate the normal vectors of the facets of this polytope. We get specific normal vectors from them. And in the spirit of what we've been talking about in these lectures, we can think of those normal vectors as G vectors. So we can think of those normal vectors as giving us G vectors for interesting cluster variables in the corresponding G4N cluster algebra. Now, I haven't told you anything about the GKN cluster algebra, but it has a very nice description. And the important point from our point of view is that given a G vector, there's a canonical way of associating with it a particular function of the momentum twistor variables or these determinants made out of the momentum twistor variables. So in this way, we can go from the geometric picture of G4N mod torus, which exists by itself, but we can sort of canonically also arrive. So this is the sense in which all the threads of these lectures sort of come together in this subject. We can also arrive at the same polytope from this perspective of stringy canonical forms. Having done so, we get a collection of vectors that we think of as the normal vectors to the facets of this polytope. We can associate each one of the normal vectors with, we can associate most of the normal vectors with particular cluster variables. And really amazingly, it turns out that some of the variables are not some of the normal vectors. In fact, 4 of them, and literally specifically what I just said, if I look at the case of G48, which is the first case where things are really interesting, 4 of them turn out not to be associated with cluster variables. So we have most of them are associated with cluster variables of the cluster algebra of G48, but 4 of them are not associated with the cluster variables. And really interestingly, the 4 that are not associated with cluster variables are associated with variables that are like delta. Okay, they're all like the delta that we saw in our previous example of winding around and all of that. In fact, there's a literal analog of that, of the delta variable that wound around that annulus. So you have to do something special with that variable. So it's really interesting. On the one hand, you get some collection, a finite collection of cluster variables associated with most of the facets of this polytope. On the other hand, you get a few new directions that you have to see if you can interpret. And on the one hand, all of the along the lines of the whole line of investigation that Mark and Nastya and Sasha Goncharov and Chris Ragu started for us a decade ago. On the one hand, we can look to see whether these functions that we can associate with the G vectors of the facets have a meaning in the amplitudes. And indeed, every one of those guys that show up has been seen as an argument of a polylogarithm in the scattering amplitudes for the 4-particle for 8-particle scattering. We're talking about G4-8, so that's n equals 8. On the other hand, some of the new directions are associated with something qualitatively new that happens precisely beginning at 8 points, that we know that the polylogarithms start including objects that are not just rational functions of the cluster variables, but involve square roots. And there's a very nice interpretation for those square roots, exactly having to do with the fact that the corresponding directions are not honest cluster variables, but are these sort of new things. Now, this is, I think, the sort of most experimental and strange part of the subject. As you see, we're now combining ideas from every part of what's going on. We start with G2n, which is just the kind of picture of endpoints on the boundary of a disk, what we see in string theory. What we care about in n equals 4 super Yang mills is like the 4 by n extension of that. And then if we want to think about think about the corresponding configuration space, it's natural to think about stringy canonical forms that go along with them. The polytopes associated with them bring to life certain particular cluster variables that are the guys that seem to show up in the actual amplitude. I think this is absolutely fascinating correspondence between all of these ideas. And even more unexpectedly to me, Lauren Williams and Tomek Lukowski and Matteo Parisi found even stranger connections between all these ideas and the literal amplituhedron, or at least the sort of baby version of the amplituhedron for the case of that parameter n equals 2. So I'm sort of rambling at the end here just to give you a sense that there's something afoot, but that these seemingly totally disconnected, naively totally disconnected subjects are really in such similar territory now that it's kind of eerie. And I'll be really fascinated to see how it all shakes out at the end. Okay, I think that is all I wanted to say about this. And as I said, it's mostly an introduction for the talks on the subject that will happen next week. Okay, so that's it.
Okay, thank you, Nima.
Do we have time for questions?
Yes, questions.
Yes, questions.
Yeah, so I'm wondering, like the normal concepts of non-abelian gauge theories, like pure gauge solutions, like instantons, and also confinement. How do they show in this this geometric description?
Good question. I mean, we don't know. I think the short answer is that when it comes to thinking about amplitudes, we have very little general. We have very little general ideas about what to expect non-perturbatively. I'll say maybe there's a few special things we can say about things like n equals 4 super Yang mills that has so much structure and integrability and so on, but it's still mostly massive numbers of tricks. If I say it really conceptually, the problem is that we don't have a priori any understanding for what. Let me try to say it simply. Let's say I handed you some scattering amplitudes, right? Say, here, I'm done. I don't tell you how I got them. I computed them somehow. Here they are. Here's a bunch of functions. We don't actually know today, in the year 2020, we don't know how to check if it's right or wrong. In other words, I can check to see if it's Lorentz invariant. I can check to see if it's unitary. I can see if I mod square everything and add them all up, if it adds up to 1. I can check that it's Lorentz invariant and unitary. What I do not know how to do is check whether it's somehow compatible with a picture of causal evolution in the interior of spacetime. That's the really hard problem. That's what we had an earlier discussion about with Richard Brower. That was really what the S-matrix program failed in. And we still don't know how to answer that question today. In other words, we don't have some first principles derivation of what the structure of amplitudes should be, what their analytic structure should be in order to be compatible with some notion of local causal evolution in the interior of space-time. We don't even know the answer to that question in perturbation theory. That's how bad it is, right? We know what it looks like at tree level. At tree level, it's very simple. The function should only have poles, and we talked about it already. It should have poles, and it should factorize into the product of lower amplitudes on those poles. We've known for about 25, 30 years, we've known what the answer looks like at one loop. However, we don't know the answer at two loops and above. Today, even today. So often, you know, people people will often ask this question at the end of talks like this. This is all perturbative. Isn't there exciting non-perturbative stuff? Who cares about all this perturbative stuff? And my answer is, you're absolutely right. There is a lot of other stuff. And that's how embarrassing it is that we don't actually understand the most basic thing about, you know, fundamental interactions in the real world, not imaginary world, you know, our actual world. We don't know the answer to the question of how to decide whether some putative amplitude is right or wrong. And there's a deep reason for it. You know, we know everything about Euclidean correlation functions and conformal field theory. You give me a conformal field theory in Euclidean space, and we know exactly what it means for it to be consistent. It should have singularities as points approach each other, and it should satisfy the operator product expansion when it does that. So no problem. It has, it's really because it's Euclidean. The deep thing about amplitudes is that it's not Euclidean. The sort of conventional way of thinking about quantum field theory is deeply Euclidean, and Euclidean space lets us essentially sidestep this whole issue about thinking about what causality and time evolution looks like. There's no time in Euclidean space. Everything is very simple in Euclidean space, and then of course, very nicely, we can, in principle, analytically continue correlation functions from Euclidean to Lorentzian signature to get the answers in Lorentzian signature. But amplitudes from the very beginning are not Euclidean things. They involve on-shell particles. They're very far from Euclidean things. They're dynamical. The time matters in a crucial way. And so while we can understand non-perturbatively how to define the consistency conditions for correlation functions in conformal field theory, and we can set up the conformal bootstrap as a very, very hard problem set problem for figuring out how to solve this. And if someone solves it, we can say congratulations, and we can decide that they're right because we can check if they're right or wrong. We know all the rules. We do not know the rules for scattering amplitude, even in perturbation theory. Never mind non-perturbative. And I think that's very exciting, of course. I think that shows the magnitude of the challenge. And my suspicion, and what I hope you've seen in these lectures, is that is that we're not going to do some very responsible thing where we sit down and derive what the rules are for causality. That's what people already tried in the 60s, and which failed so miserably. What we're going to do instead is discover these fascinating structures of the sort we've been seeing, and probably many, many more things besides, and eventually understand where causality and the space-time and the rules of unitary and all these things come from. It's going to be an output. It's not going to be an input. And hopefully when that happens, we'll have a very different perspective on what's actually going on. So that was a long answer, but I took it as an opportunity to explain this very important zeroth order point that you want to know about but just to push the point. Even the way that often these questions are framed, like what about instantons in your way of thinking about things? Actually, what about instantons? Instantons are not a physical part of the instantons are a Euclidean solution. It's a Euclidean solution that captures certain non-perturbative effects by some contour deformation broadly speaking, by some contour deformation in the path integral picture. So the question isn't so much where are instantons, it's more physically where are these non-perturbatively tiny effects that are associated with instantons from this other point of view. And the short answer is, well, we don't know because we don't even know the answer for what the rules are supposed to be in perturbation theory. I think that's my long answer to your question. If the question is where are all these non-perturbative effects, the answer is we don't know right now. We don't even know what's happening at sort of two loops and above in garden variety theories. And I think this is an indication of the sort of richness and depth of these problems that, you know, going into the second fifth of the 21st century, we still don't know the answer to these questions.
Thank you. And can I ask you another question? So at first I asked you about the about if in this geometric picture we can see this IR cancellation, IR singularity cancellation in Yang theory, and then you said that in the lecture you're gonna mention that.
No,
Maybe you mentioned that I missed.
No, great. No, I didn't mention it. Thanks for bringing the question up. Yeah. So, in fact, yeah, it's an important enough point that I want to go back to the slides for a second. So, what is the relationship? So we've seen, at least broadly here, we have for gluons. Oh, can you guys see? Maybe you can't see. Hold on, let me share again. Let me share again. Okay. All right, good. So we have for gluons, so all this geometry crap, we have one story kind of for gluons, whether it's maximally supersymmetric or not. And this is the story of the amplituhedron. And now we have something else for this phi cube theory, and this is the isosahedron. And what I want to do is sort of describe at least roughly how these things are related to each other. As we've seen, the actual kinematical spaces are quite different. I've stressed already a few times, this space is about pairs like pi.pj. This is something quite different. So there's some details that are different. But on the other hand, let's go back to our friend, the experimentalist, at infinity, and ask what they would think if they had the amplitudes for gluons instead of the amplitudes for phi cube theory. And you see, what this experimentalist at infinity got excited about was the poles of the amplitude. And then instead of talking about factorization, they just kept going to look for more and more poles, right? That's the thing that we had talked about. And the remarkable thing is that there's a geometry that controls the combinatorics of how all the poles come together, right? That's what we talked about. So the isosahedron is about the sort of most universal for any theory, universal, totally universal factorizations, which eventually go down to cubic diagrams, right? No matter what we do, eventually we go down to cubic diagrams. Every theory in the world has these singularities. Every theory of the world has these poles, and so that's why it's sort of remarkable. There's something universal about how the facts are captured together in a geometry. Okay? However, the theory of gluons has even more singularities that you talk about that are not there in totally garden variety theories, but are really just there for the theory of gluons. And in fact, gravitons have even more, but we're not going to talk about gravitons. We're not going to talk about gravitons here. What are the singularities that gluons have that scalars don't have? They have soft singularities, and they have soft divergences, okay? And so, in fact, if we let's just illustrate the sort of richness of what is going on. Let's say we just talk about 4-point scattering. And if we have 4-point scattering for scalars, we've already said that what we have is just 1 over f plus 1 over t. Okay, so if that's all we have, if those are the only singularities we're talking about, then we just have one pole, we have a one-dimensional geometry, and that's it. It's this one-dimensional isosahedron. That's all, right? However, the scattering amplitude for gluons, if these are now gluons, now it's more interesting. If we know about amplitudes, you know that you get the Park-Taylor formula. So if you do this supersymmetrically, if you know about this, just so I can focus on the interesting part, there's a supersymmetric part upstairs, and then there are all these poles downstairs. And so you can have more singularities just than s goes to 0 or t goes to 0, because, and you can see that here, because I have these poles that have to do with these two-dimensional vectors. Okay, so there's a 2 vector for the lambda 1, lambda 2, lambda 3, lambda 4. And the Park-Taylor amplitude has singularities when any of these things go to 0 as well. In fact, if you look at this amplitude, it looks exactly like the canonical form for the positive Grassmannian of G24. And that's in fact exactly is what it is. So the space of possible poles that you can take is not just one-dimensional, it's four-dimensional. It's four-dimensional because we have all these soft singularities we can take as well, where we make lambdas parallel and then we send the momentum to 0. Those are extra singularities that we see for gluons that are not there for the phi cube theory. Okay, all the singularities of the phi cube theory are also there for the gluons, but the gluons have more. The gluons have more. Okay, so if this experimentalist at infinity were to do their exercise with gluons, they would find many more poles. If they were really obsessive about it, they would really find a much richer structure of poles, and they would discover, they would still do the kind of counts that we talked about, that see these interesting numbers. They would take alternating sums of these numbers and find something that had patterns in them, but they would try and try and try, and they would fail to fit this pattern of singularities that includes the soft singularities. They would fail to fit them to some kind of polytope, like they could to the isosahedron. In fact, they would fail because it's not a literal polytope, but it is a positive geometry. The geometry that captures this universal physics that includes the soft divergences for gluons is the amplituhedron. And that's the relationship between these ideas. So there is a positive geometry, a polytopal geometry that's very universal, too universal, phi cube, any old theory that just has factorization. But if you want to see the further singularities that are associated with IR divergences and all the other things that we're talking about, you need to see the soft singularities too. And that greatly enriches what the structure of singularities looks like. So that instead of having just a simple polytope like the isosahedron, you have this fancier Grassmannian generalization of polytopes into the amplituhedron. Okay, so that's just to say that both the amplituhedron and the isosahedron are showing us that there's some hidden combinatorial structure in the sort of long distance factorization type singularities with scattering amplitude in the real world. Gluons, scalars, anything, the universal part is there in the isosahedron, and there's this more refined, deeper part that includes things that are special to gluons that we only see when we further lift from polytopes to the world of Grassmannian generalizations of polytopes like the amplituhedron. I mean, I didn't talk about the amplituhedron in detail in these lectures. I talked about it a lot in the sort of marathon lectures last year at Davis. So I thought I'd talk about a different subject, a somewhat different subject this time. But just to say that at this point, all this business with polytopes is really cool. It's really interesting. There's a huge amount to understand. But these things are like the level of sort of depth and sophistication of the ideas involving the amplituhedron are like a couple of levels higher than this. There's really a lot more going on. I mean, that's really a completely mind-blowingly interesting object. It's going to take a long time to figure out what it's really trying to help.
Can I ask a question?
Sure.
Yeah. You said in the start that you will not comment on the cosmological correlators and the amplitudes story in that sense. So can you comment that some of the story that you learned today will, I mean, are there parallels between the two approaches, and what could be the main differences?
So let me just say something. First, a very broad point here. Okay. If we think about just the development of our understanding of amplitudes, people say this a lot. Mark, especially, is quite eloquent about this. What do you call it? A virtuous cycle? I forget what it's called. That this is the general subject of amplitudes is really wonderful because it has on the one hand, there's all this fancy schmancy stuff, and you can say all these highfalutin words, at least the way I like to talk about it. On the other hand, you cannot bullshit. There is zero bullshit in this subject. It's not just about slogans and blah. You have to actually calculate something, and you can check if you're right or wrong. Okay? You can really check if you're right or wrong. And so no one will tolerate anything, and you will tolerate it, at least of all, if you're just sort of BSing and doing some qualitative thing, blah, blah. Things work or they don't work. And so anyway, so the progress is driven by learning how to calculate things by any technique you can, by hook or crook. And then after you gather a lot of theoretical data, maybe you can step back and see if there's an underlying structure that explains some of it, which might allow you to calculate even more things, that then the cycle continues. That's the sort of virtuous cycle aspect of things. And this virtuous cycle in this field has been going on for like 20, 25, 30 years, depending on when you start counting. So there's by now really an ocean of theoretical data in many different aspects of the subject, some more than others. For example, our understanding of massive amplitudes is just in its infancy. Gravity is still really just in its infancy. As I mentioned before, there's obviously so much more to understand in gravity than sort of merely this thing that's like gauge squared, which is just a tiny part of the story. So there's really a lot to be, there's still other things to be understood, but there's still an ocean of things understood about gluon amplitudes, all sorts of different things. And the physical philosophy driving this is what you can think of as the on-shell perspective. You want to throw out as much as you can all the unnecessary baggage, gauge redundancies, fields, Lagrangians, and just find some way to, again, it doesn't have to be fancy schmancy geometries, blah, blah. You can just make some ansatz what the answer is that has the kind of singularities you want and then determine the answer. That's one of the most tried and true first ways of going about doing things, and was and continues to be a fantastic way of generating data and making progress. So this on-shell philosophy that you try as much as possible to not use some extra formalism, but just directly try to figure out the properties of the answer, the singularities of the answer that need to be fixed in order to determine it. The answer has been one of the engines that has driven just the gathering of theoretical data and the ability to do computations in this subject for a long time. Okay, now we can move to thinking about cosmological correlators and the calculation of cosmological correlators in Flake.
We don't hear you anymore.
Yeah, we lost your voice.
Apparently he can't hear us either.
Oh,
Nima, we can't hear you.
yeah, Nima, we can't hear you.
Is he okay?
And somebody just turn on their video and like wave or something.
Yeah, that would be a good idea. Hold on.
Let me try to unmute him. Manually.
You saw that.
Yeah, what happened?
We didn't hear you.
Oh, sorry. Whoa. Is that okay? Can you hear me now?
Yeah.
Okay, great. Sorry about that.
Rewind 2 minutes, Nima.
Oh, okay, sorry. Well, okay. I just want to say that I just think that yeah. So this on-shell attitude towards calculating amplitudes has been the engine that has driven the gathering of theoretical data and lots of progress. And again, the whole idea is to not rely on some formalism or fields, Lagrangians, but just kind of directly get to the heart of what's interesting of the singularity structure of the objects you're interested in, and try to use them and other physical constraints however you can to get to the answer. That's a story for amplitudes. And then there's much else besides. After you get a lot of that data, you can look for some underlying mathematical structure, go back and forth, and that's the game that we've been playing from many angles for a number of years now. The story in cosmology, I would say sort of cosmology is where amplitudes was 25 years ago. And everything is sort of one order of magnitude harder. So if you imagine trying to do like the Feynman diagram computation of correlation functions is ridiculously hard. An example is if until a couple years ago, no one had an explicit formula for the tree-level exchange of a massive scalar in de Sitter, in inflation, something that you might hand an experimental friend to go look at, concretely, specific formula to look for the possible tree-level exchange of a massive scalar. Of course, you can trivially do the Feynman rules and write it down. The problem is that you have all these integrals over time with terrible Hankel functions, and if you're just like out of the box shoving it in, it just looks complicated. Looks very complicated. But you can take the same on-shell philosophy and say, okay, forget the formalism. What's really going on? The answer is certain symmetries. The symmetries are, if I have inflation, it's the symmetries of the underlying de Sitter space. That means that the correlation functions are conformally invariant. And again, you can think about conformal symmetry. You can think about what kind of singularities they can have. Again, you can have the same experimental theoretical attitude we have in amplitudes to kind of begin this program of systematically thinking about cosmological correlators. Okay, so that is a story, at least an aspect of the story that Juan Maldacen and I talked about a number of years ago. The more systematic version of it, literally along the lines of what we do with amplitudes, was in a paper I had with Daniel Baumann and Hayden Lee and Guy Pimentel, and those guys have been pushing it a lot since, and they're going to have another beautiful paper about it coming out soon. But it's still just at the point of sort of nailing what we understand about the 4-point function for tree amplitudes. Okay, so that's what I meant. It's like where amplitudes were 25 years ago. So what's needed in that subject? I think it's very exciting. I think it's really cool and very, very beautiful. What's needed is to just first go and think. Now they understand things pretty well at one loop. How would you think about things at tree level? How do you think about things at one loop? What's the analog of the box decomposition? What's the analog of dispersion relations? What's the analog of the Challen-Layman representation? I mean, every simple basic thing about amplitudes, never mind fancier things, is not known. Is there an analog of the Park-Taylor formula? It actually looks like there is a beautiful analog of Park-Taylor, something we've been discussing for a little while. But anyway, I'm just giving you an idea that it's just where amplitudes were like 20, 25 years ago. So I think to really see, I suspect to really see some kind of amazing geometry coming out or something like that, we're going to need to see more data. But people are impatient. I'm impatient, and so a number of years ago with Paolo Benincasa and Alex Posnikov, we've seen some kind of very baby version of these ideas like the amplituhedron and the icosahedron in the context of cosmology. There's something we call cosmological polytopes, and the reason it's very baby is that unlike the things that we're talking about here that are really about the whole amplitude, you look at the entire tree amplitude, or even for the integrand, but it's not about one Feynman diagram. It's about the whole shebang. Here, things are so hard in cosmology that even a single Feynman diagram is really complicated. And what we found is that a single Feynman diagram, the answer from a single Feynman diagram is actually captured by a beautiful polytope. And that, in fact, you can sort of go backwards and forwards from the polytope to the Feynman graph, from the graph to the polytope. So that's some indication that some of these ideas are going to extend to cosmology. A deeper reason that the ideas have to extend to cosmology, and this is one of the, I think it's an absolutely amazing thing. It's technically basically trivial, but it's physically really remarkable, is that cosmological correlators actually contain inside them scattering amplitudes. So they're not like totally independent things. This is actually such an important point. I want to go back to my, I want to go back if you don't mind. So, when you do calculations in cosmology, the sort of big difference is that, we draw Feynman diagrams. Like, let's say you want to have some kind of correlation function. We're making the measurement here at future time. Often people write as conformal time equals 0. But anyway, we have some correlators. These are spatial correlators. They're points in space. Okay. So we're looking at some correlation function here. And we imagine that there's some sort of Feynman diagrams or something like this going on in time. Okay, so, but the actual observable is only a function of spatial coordinates. but we still have translational invariance. So whatever we have up here, so this is just the thing that I'm computing, and maybe it's coming from this diagram or some much more complicated diagram. Whatever I'm computing is, for example, density perturbations is a function of a bunch of position coordinates. And so because of translational invariance, if I Fourier transform, it's some function of n momenta, k1, k2, up to kn, where the sum of the k's is equal to 0. Okay. Now, if you look at this data, so that's the data. That is the data, and you see the data looks almost identical to the data for a scattering amplitude. That's exactly what the data for an amplitude looks like too. It has momentum conservation. It has a lot of particles. All the spatial momenta have to add up to 0. However, there's one thing missing here that we do have for amplitudes. For amplitudes, we have not just that the sum of the spatial momenta is 0, but also the sum of the energies is 0, because we have time translational invariance. In cosmology, we don't have time translational invariance. We are doing these measurements on the spatial future. So we draw Feynman diagrams like this, say, who knows? But we don't have time translation invariance, so we don't have the analog of energy conservation, right? So in other words, amplitudes look like some function of k1 up to kn, and also a delta function for e1 plus the en. Correlation functions just look like some function of k1 through kn, and they don't have this delta function for energy conservation. But here's the amazing thing. They do contain pieces that have instead a pole in the sum of the energy instead of a delta function for momentum for energy conservation. And I can explain where that comes from very easily. Imagine you have just a very simple thing like this, like a 5-5-4 interaction. How would I compute this? Well, if I'm doing this calculation now in time space, not frequency space, because I don't have time translational invariance, I might as well do this calculation in time space. Then I'm supposed to integrate over this interaction vertex. All these propagators are just the free solution of the wave equation. So I get an e to the I energy 1 eta, e to the I energy 2 eta, blah, blah. E to the I energy 4 eta in this case. So I would get an integral d eta, and this integral goes from minus infinity to 0, d eta e to the I, the sum of the energies, times eta. So this is not, okay, so I get an integral minus infinity to 0, d eta, e to the I, the sum of the energies. Versus what I'd get for an amplitude. For an amplitude, I would have an integral minus infinity to infinity, d eta, e to the I, the sum of all the energies, eta. This gives me a delta function for energy conservation, whereas this gives me just the pole, sum of one over energies. Now, here energy just means the magnitude of k. They're no physical particles. I just mean the magnitude of k. But you see that the correlation function has the structure of a function of momenta, and it has something which, if I appropriately analytically continue, I mean, for physical spatial momenta, these are all positive, so I can't get a pole. But if I analytically continue, so that this can go to 0, then here's the amazing sort of obvious, technically obvious fact that when I do this analytic continuation of the correlation function, on this total energy goes to 0 pole, what I get is 1 over E total, and what it multiplies is the actual scattering amplitude. You see, when you go on the pole, you do have energy conservation, and so the residue of the pole now has energy conservation too. What else could it be other than the scattering amplitude? This is, I think, absolutely amazing, because it means that cosmological correlator, something you could measure by lying on your back and looking at the sky. These static measurements have in them, by analytic continuation, of course, but they have in them all this dynamical information about particle scattering. In other words, scattering amplitudes are a special case of cosmological correlators. They're a special case when you analytically continue to this place where the sum of the energies is equal to 0. Given that that's the case, and given all the magic we've seen in scattering amplitudes, it is, I think, just inconceivable that that magic does not extend to cosmological correlation functions as well. How can it be that all this crazy geometry, blah, 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 all this amazing stuff, even all the different stuff we've been seeing, how can it be that that's restricted just to this codimension 1 surface in the space of everything we can see for the cosmological correlators? There's no way. So that's why I think it's totally obvious that there's going to be an enormous story there. But you should sort of think about it as where amplitudes were 25 years ago. All right, that was a very long answer to your question, but thank you for asking.
Thanks.
It gave me an opportunity to say a few other things.
No, thanks a lot. Very elaborate.
All right.
Thanks.
All right. Are there any other questions?
There are some good questions out there, Nima, but we're worried about liability if you crash.
I mean, if this is secretly because you want to, or even not so secretly, if you want to go, be with your loved ones, that's fine. That's no, I'm doing okay.
So Nima, I'm a non-expert, and thanks for all the talk. I thought there was a couple of hours from 10 to 12, but I guess you meant midnight. Going back to what you were talking about, like, I mean, the Grassmannian, and you looked at it sort of a column sort of view of it.
Yes.
Have you looked at sort of row version of it? So the K by N.
So. Very, very much so. In fact,
can you talk about that? Because I mean, I was thinking about it when you're talking about it, and like I was thinking of what does it mean, like
Yes. If you look at there's the if this was a talk about Grassmannians and amplituhedra and things, I think I talked about some of these things, for example, in the set of lectures last year at Davis. There's a whole thing about how the column and row vector, the column and row views of Grassmannians are related to each other. Absolutely. And there's actually really a fascinating story there. In fact, the entire connection between, I mean, I'll just tell you a tiny bit about it, just so you have a flavor. So something that we know is that so if you want to know why do these weirdo Grassmannians have anything to do with scattering up? Just at 0th order, why is there any kind of connection of this sort at all? Never mind all this fancier things. The reason is sitting there right at the beginning in how we think about on-shell momenta. So we think about on-shell momenta for massless particles in 4 dimensions as given by the product of these spinor helicity variables. And so each one of these variables is just a 2 by, so lambda is like A1 is AB. Lambda tilde is A tilde B tilde. And there's an action of an SL2 that acts on these guys and another SL2 that acts on these guys. So if you want to give me all the data for the particle scattering, you have to give me lambda 1, lambda 2 up to lambda n, and also lambda tilde 1, lambda tilde 2 up to lambda tilde n. So naively, again, you're giving me n column vectors, A1, B1, A2, B2, up to AN, BN. And similarly for the other guy. All right, but now the fun begins. Let's think of this, so let me give this guy a name. Capital lambda is like A1, B1 up to AN, BN, and capital lambda tilde is A tilde 1, B tilde 1 up to A tilde N, B tilde N. Now let me think about this, even though it was given to me as as column vectors, let me think about it as 2 row vectors instead. So I want to think in this language. So what am I doing? It means that I imagine there's this giant row vector A, and this is n-dimensional space, and there's some other row vector B in this n-dimensional space. And now let's ask what happens to a different Lorentz observer. A different Lorentz observer, the action of Lorentz transformations is SL2. So that means that in a different Lorentz frame, I'll get some different A prime and some different B prime. But there is something that's invariant. And the something that's invariant is the 2-plane that's spanned by them. So you see, once you start thinking in this row way, here there's one 2-plane, here'd be another 2-plane. The bases for these 2 planes would change from Lorentz frame to Lorentz frame, but the whole 2-plane itself would be invariant. So that's the beginning. Exactly this picture of going from row to column vectors is the beginning to thinking, to seeing why there's some kind of connection between amplitudes and something, funny seeming like the space of two planes in n dimensions. And in fact, momentum conservation is a beautiful thing in this picture. Momentum conservation says that the sum of lambda tilde is equal to 0. Well, that means something. That means that I have this two-plane. I'm going to draw it a little badly now. And there's another two-plane. So there's a two-plane lambda. There's another two-plane lambda tilde. And momentum conservation is really the same. They have to be orthogonal to each other. Okay, so we see that something as basic as momentum conservation, first thinking about momenta, brings to life this two-plane for lambda, this other two-plane for lambda tilde. They have to be orthogonal in this interesting way. And beginning with this observation and running with it, trying to make this orthogonality manifest and exploring it more is the lead, following your nose to the entire story that connects gluon scattering amplitudes, n equals 4 superunion node to the positive Grassmannian, and later to the amplituhedron. So this, I think it's one of the things about this subject is incredibly basic questions. If you take them really seriously, if you try to sort of represent things and think about them in the most invariant way possible, they can go very, very far. And exactly this business about the row versus column way of thinking about Grassmannians has actually played a significant role in a number of aspects of this story.
Okay, thanks. So looking at it column-wise, there's a connection to cluster algebra, but
That's
looking
right.
at it row-wise, is there also a connection to cluster algebra? Or I mean, has anybody done a lot of work on this? Like it seems that.
Well, along those lines, I can tell you the following thing. If you think about I think at a deep level the answer is yes, and it's related to a subject that a scary and deep subject known as the Lustig canonical basis. This is something that I don't understand at all. Well, I mean, I understand somewhat, and even my best mathematician friends will do their best not to try to explain it to me because they know my brain won't be able to take it. But anyway, if I give you a rough idea about it, there's a picture for what the positive Grassmannian is, which the sort of picture itself is about columns. Even though we're talking about planes, it is about columns, and it's the one that I described. You take a k by a matrix, you take the determinant of k columns, and you ask for it to be positive. So in that picture, you care about the k, you care about the columns, and you care about these minors. There's a totally different picture, which is that you start from some representative point in the Grassmannian. Any representative point you can think of as an identity k by k block and zeros everywhere else. And then what you do is you do linear transformations. In other words, you do GLN transformation. So that works in this direction. So that's working in the direction of the row. It's sort of moving things around in the row rather than thinking about k by k transformations on the column. So the entire story of total positivity, or the modern story of total positivity, really begins with Lustig, and that was his way of thinking about it. Is that you start from a general point, and then you allow yourself only special kinds of GLN transformations with some positivity properties to move you around and make everything. That ends up being non-trivially related to the other ways of thinking about it in terms of the minus all being positive that Postnikov and other people talked about. Now, it's really cool that the relationship between these two pictures is something that's very familiar from the physical point of view, because the picture of moving columns around by shifting them by their neighbors is exactly what happens with BCFW recursion relations. And that was one of the entry points into this whole connection with the Grassmannian. So, roughly speaking, the fact that the Lustig way and this minor way of thinking about total positivity are related is conceptually related. Well, I mean, it's the same surprise that the kind of objects we got from BCFW recursion were associated with the cells of the Grassmannian, where minors where you could start sending minors to a zero. So that level of connection is something where you care about what's going on in the rows, So there is some aspects, there are some deep aspects of total positivity related to that, but I don't understand it. I don't understand it well myself.
Thanks. That's super cool. So I'll let other people ask questions, but your explanation brought a whole bunch of other questions, but I'll let other people ask questions.
I guess I'll ask the question that I posted into the comments. So going from GR48 to Grassmannian 48 to Grassmannian 49.
Yeah, right.
It's no longer mutation finite. So you're missing, you're not just missing.
Right. Well, let me say, I'll take the opportunity to say a little something which I didn't say. So I can at least give you a toy example. So so first of all, it's true that in this kind of story that we're talking about, where you can think about GKN mod torus, we can do it for any KNN. 4,9 is fine. Anything is fine. It's not obvious. It needs to be looked at. It's not obvious whether, if we take the polytopes that we get from this tropical positive Grassmannian perspective, the canonical form perspective, whatever we do, who knows what we're going to get? I don't know what we're going to get. Could it be that there's some intelligent, maybe out of the box, even though it doesn't have to be, everything that we get, we can still sort of canonically associate with, we might still be able to canonically associate with, if not rational functions, at least algebraic functions, the way we've already done with G4A. It could be that that's not happening. And maybe if that's not happening, that's a reflection of the fact that eventually, certainly starting with 9 points, we expect to see elliptic things in the answer. So maybe that ellipticity is going to be related somehow to this wilder thing that we expect. So I think the short answer, as anticipated by what Mark wrote there, is I think we don't know, but yeah, we need to explore. Let me say one thing here, though. You could ask the following question, and I mean, I've asked it. Mark and I, well, we've all talked about it. I've now, I said in these talks that there's this general difficulty of taming the infinity, right? We've got to figure out how to tame the infinity. And there's a taming the infinity problem for the phi-cube bi-adjoint theory, and that has to do with the surface cluster algebra of that infinity. And there's the taming the infinity associated with G4N. And of course, they're different. At least the surface case is a little bit tamer because it's finite mutation type. Something is different is happening in the G4N case. But it's kind of curious that the strategy for the taming that we found for the surface case, where we include delta and we do all the things that I was telling you about here, is really not the same as the strategy of playing with the stringy canonical form. So it would be interesting to see if there's any kind of analog of the strategy that we've seen in the sort of small examples that still have this affine character to them in the surface cases, but whether something like that might work for G4A, which also still has this sort of affine sense about it. The reason I bring this up is because at least we can see in very small examples, in this other way of thinking about things, we can see what you can do in the wilder type cases. So let's say we go back to this really simple example where we have 3 arrows, okay? So again, just this little 2-dimensional geometry, as I told you, now there's an honest hole here, and that's it. So there's some limiting rays in both these directions, and there's an honest hole here, okay? So what can we do? There's no unique delta anymore. What's going on? Well, it turns out, at least in this example, and then there are cousins of this, but certainly in this example, it turns out that, okay, there's a hole, but there's more than one delta in here. Okay, there's actually a collection of deltas. And in fact, if you want to include more and more guys on the outside, you've got to include more and more deltas on the inside. But there's a canonical way of doing it so that everything still beautifully works. Okay, so that's an example where there's really life in this hole, and the life in the hole sort of mirrors the life outside it. And yeah, whether something like this can happen, this is a trivial, tiny example, but whether something like this can be of relevance to these much larger examples that we need for n equals 4 really remains to be seen. As you know very well, the kind of real challenge is that the smallest examples where something new happens are just so giant in n equals 4 that you can do what we've been doing and what people have been doing. I think it's wonderful to explore, try to see patterns. I mean, that's what we should do. You're better doing that than sitting on your hands, for sure. But at least to my mind, there's still not there isn't a conceptual picture for what's going on at all, and it's difficult to get one because the examples are so big. I hope that with more work and trying to see more patterns, we'll start being able to focus on sort of smaller problems that are a little more amenable to be sort of thought about with our brains rather than just with the computer.
Thank you. Oh, that was great. Can I ask one more quick question?
Sure.
If no one, so you mentioned it before, and I had a quick question on it in the chat again. When you were talking about the affine surface algebras, I was thinking about Gayoto's paper, and you were talking about with the counting BPS states and like Donaldson invariants and stuff.
Yeah.
Do you think, is it feasible that I can like really interpret what you're doing in that context of like wall crossing formulas, Gromov-Witten invariants, like that kind of thing? Do you think that's like a reason?
I mean, I don't know a lot about this. I don't know a lot in detail about this subject, but at this point, I would just be absolutely shocked if everything isn't related to everything. I realize it sounds like Pollyanna, but actually, it's not as crazy as it sounds. There's already. So you could say, well, this cluster thing is some deep thing going to show up everywhere. Fine. And there's the way it showed up in the guide to Moore-Minsky's story. But that stuff is directly related to amplitudes, n equals 4 amplitudes at strong coupling, which is what Maldacena, Gayoto, Vieira, other people, Sever, explored a lot already 10, 12 years ago. So all these Y system equations, all the stuff that came up in the context of the wall crossing story, the same equations control the soap bubble picture for scattering amplitudes or Wilson loops at strong coupling in the ADS. So it's not like only vaguely related. It's literally computes amplitudes at super strong coupling at the other end where the string picture is good. I want to make another sort of qualitative point that it really seems like there's some kind of duality at work here. The story of the integrand is about G4n. Or this winding G4n. But anyway, it's without mod torus. The story of the amplitude knows about something about modding by a torus. And the relationship between these two things is not trivial. It seems to involve something like a duality. I've had a fantasy for a long time that we know what the G4n without modding by torus is about. G4n and its winding cousins in the amplituhedron is some more abstract way of talking about gluons in the end. Even though we don't see Feynman diagrams and all of the rest of this stuff, in the end we get these integrands, and they're the integrands for gluons. And we can recognize that they're about gluons by seeing their singularity structure and all the rest of the stuff. Okay, so we know what one part of the story is about. We have one part of the story. So we have gluons on one side, and this is tied to the amplituhedron, which is ultimately about this G winding K, M equals 4, and N space. Okay, now, on the other hand, there's something on the other side here. There's something here. Now, I think there's various mysterious beasts out there that it might be. There is something that I think about all the time, what the dual amplituhedron, or this more concretely, perhaps, this GK M equals 4N mod P space and so on. Okay, so that exists, and we don't quite know what the connection is between them, but it's not trivial. And there is some structure on this side, and the question is, what is it about? The structure here is about gluons. Well, it seems very reasonable to me that this structure is really meant to be about strings. That's the way we'll see sort of gauge gravity duality, or gauge string duality in this case anyway, as kind of a consequence of this more primitive mathematical duality between something we understand pretty well on one side, not very well, but still pretty well on one side, and something that's much more mysterious on the other. But anyway, it's a pure fantasy. But I think it would be a really fascinating thing for things to work out. That we've already figured out how to sever the connection to normal physical notions in this direction. We have this sort of more invariant object that we're trying to learn and understand more about. And then we can see that in some ways, that we can think about it in certain ways to reduce to what looks like gluons. Well, it'd be amazing if there's a natural sort of mathematical duality that relates this to the other space, and that there's some cousin of the map that we've seen on this side that makes it look like strings. And the fact that the Y-system equations and all that stuff really turns into strings at the other end is very strongly encouraging of such a fantasy. It's only a fantasy, but it's after 10 o'clock, so it's not bad to it's allowed to share some.
Thank you. Thank you.
Nima, on that note, usually in your talks, you have at the beginning of the talk a list of approximately 7 ongoing projects. And then due to time constraints, you only managed to talk about one of them.
Right.
So today we've heard about the all loop phi cube story with Giulio and Hadley.
Right.
But what are some other specific projects that are on your to-do list to be finished soon, hopefully?
Well, I can tell you there's something that I think is really, really interesting, but it's not soon. I mean, we've just started getting into it, but a little more seriously getting into it. So we're really trying to understand things in detail. But it's in a completely orthogonal direction to all of these things. So along the lines of the broad picture we're just talking about, all of these amazing geometric things we've been talking about are about infrared, long distances, factorization, all of that, right? As I've said many times in amplitudes talks, summer schools, and so on, if you ask me, what am I worried about in this entire approach to a physics? What do I think might be a showstopper? What I'm worried about is the renormalization group. In other words, I'm worried about ultraviolet divergences, the whole way we organize our thinking about physics, the Wilsonian way of thinking about physics, which is so amazing, it's so deep, it's so important, is also the most off-shell local quantum field theory Lagrangian thing there is, okay? So if I say it another way, if you're going to, just to exaggerate, if you're going to sit there trashing standard local quantum field theory because it sucks for amplitudes calculations, it's so complicated, blah, 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 that's fine. But you're like, if local quantum field theory is the enemy, you're attacking the enemy at its weakest point when you do that. Because after all, it's a historical accident that local quantum field theory was developed in the hands of Feynman to calculate scattering amplitudes. Local quantum field theory doesn't really like scattering amplitudes. It likes local correlation functions in Euclidean space. That's what local quantum field theory likes. And the entire picture of the Wilsonian renormalization group, the Wilsonian way of thinking about the world is deeply Euclidean, very far from amplitudes. You're supposed to zoom in on a point in space-time and gradually zoom out, change your resolution, all of that stuff, organize your thinking about physics by scale, all of those things. And of course, in an earlier life, still, effective field theory is maybe my favorite thing in all of physics. So it's always worried me in the back of my mind, how are we going to understand the renormalization group from this on-shell point of view? We don't have access to this idea of zooming out, off-shell, integrating out shells of momenta. And so it's like sort of attacking the enemy where it's strongest, which is really what you should be doing. If you're going to talk about some fancy way to calculate amplitudes, well, that's a very non-local question to begin with. It's not so surprising that field theory is not as awesome at it as it is for things that look genuinely local. So So that's, I think, a really deep and important question. There are many concrete avatars of it. For example, the most concrete thing of all, what we get from the renormalization group is an instant prediction that if you do a one-loop calculation and you extract the coefficient of the ultraviolet logarithm, you instantaneously know the answer to a 100-loop calculation. That the leading logarithms are determined by what you get at one loop, and the subleading logarithms are determined where you get at two loops, and so on. Diagrammatically, purely as a fact about the computation, that's not obvious at all. If you ask, is this obvious, much more basic things, are they obvious from amplitudes? Is it obvious that if I look at the coefficient of the ultraviolet log at one loop, if I compute it using on-shell methods, is it obvious that it's even proportional to the tree amplitude? It's not obvious. Okay, so there's some clear challenge there to try and understand things. But I thought one entry into the subject is that this whole story of Hopf algebras that control the renormalization group, and Kahn and Kreimer and Francis Brown and other people looking at these things, they have found some geometry associated with the ultraviolet divergences and the renormalization group. And Francis was telling me last September about something called the Feynman polytope that's naturally associated when you do calculations in Feynman parameter space. And he told me that the Feynman polytope has remarkable properties. When you go on the boundaries, it factorizes into lower Feynman polytopes. And that fact is the ultimate origin of the Hopf algebra structure, the RG, and all the rest of it. So anyway, with Sebastian Vizera and Aaron Hillman, we're just studying this, starting to try to understand it from our own point of view. And I think it's really fascinating. I don't know where it's going at, but I think that there's really something there to try to connect. So they would say that yes, there is a better way of Wilson than thinking about things, and the better way involves precisely the existence of certain geometric objects that have this very similar properties that we've seen for amplitudes. They factorize the similar things on boundaries and so on. And they would say that this is just as good, if not better, than the Wilsonian way of thinking about things. So if that's really true, and if we understand it, and we can figure out how to connect it to the rest of what we've been seeing, I think that would really be amazing. So it's not something coming out anytime particularly soon, but we've been doing a reasonable amount of work on it, and I find it quite exciting.
I was wondering if there were some connections to number theory, in particular monstrous moonshine, and then a little bit on a separate topic. What about graph theory?
Monstrous moonshine, I don't know per se. I don't see one, but I don't know a lot. I mean, I know about that at the sort of lay level that a lot of people do. I sort of doubt it. Graph theory. It depends what you mean by, yeah. I would say sort of no, except for the fact that some sort of very basic facts about the kind of graphs we see, these planar graphs, electrical networks, Plavik graphs, they play a kind of an important role in a lot of this subject. But I think sort of fancy things about modern graph theory, Ramsey theory, what random graphs look like, where graph theory is in the 21st century is not playing any role in this subject so far as I can tell.
Okay, thanks.
Oh yeah, Nima, I was going to add, I wrote in the comments that the question about number theory opens the door for you to tell us about finite field methods and their applicability for.
Yes. Oh, I would love to do that. Actually, so there is a stack of things along those lines that are going on, and so in the answer to your previous question, I really wanted to talk about something mention something really quite new that we've not been thinking about before. But indeed, there's all sorts of aspects. There are developments along the lines of the things that have been going on with these binary geometries and our stuff and a number of other things, and many of these things have a connection to, at least there's some very interesting connection to finite field methods. So, okay, let me say a little bit about this. This is actually, I think, a nice open problem. I would love to spend some time thinking about. Actually, before talking about finite field methods, let me just mention that well, actually, I think maybe I'll just mention this. I'll mention this kind of open, I think, open, interesting direction, research direction. There are some recreational things about finite field methods that might be useful later. I'd be happy to talk about them a little too, but let me mention something I think is slightly deeper. So we've seen that we can think about these generalized, these string amplitudes, and even these sort of cluster generalization of string amplitudes, and they all have the sort of character of an integral over some space. Like, for example, even for string amplitudes, we have the integral over G2n mod torus. We have this canonical form, and then we regulate it with the product of all the minors to some alpha prime side j. And then we have analogs of this for other Grassmannians, cluster algebras, more generally, and so on. Okay. Now, so even in the simplest case of the beta function, we have an integral 0 to 1 dx over x1 minus x, x to the alpha prime a, 1 minus x to the alpha prime b. So now, there's a natural number theoretic counterpart to this, which is very well known. It's been studied since the 1800s. They're known as Jacobi sums. And let me just give you an idea of what we're talking about. First, for those of you who don't know what finite fields are, well, you know what fields are. They're just something where you're allowed to just do all the ordinary operations of arithmetic. Can't divide by 0. But you want to do it on something with a finite number of elements. So the first thing you might want to try is like modular arithmetic, but you don't have the usual rules of arithmetic, because, for example, 2 times 3 is equal to 0 mod 6. So I can't just say I'm considering things mod n, because I can have the product of 2 non-zero things equal 0. However, it's very easy to see that this doesn't happen if you're working modulo or prime. If you work modulo or prime, basically the kind of first fact about numbers known to the Greeks, the Euclidean algorithm and so on, if you have AB, if AB is equal to 0 mod p, then either A equals 0 or B equals 0 mod p. So this is a slightly non-trivial fact that's then responsible for unique prime factorization. So it's not the other way, really. This is the basic fact from which unique prime factorization follows. And anyway, the reason this is true is very simple. It has to do with the Euclidean algorithm and so on. But it means in practice that working modulo p, everything has an inverse. Obviously, I can add, I can multiply, and any non-zero element has an inverse. So I can have A times B equals 1, mod p has a unique solution. B equals A inverse is unique, mod p. Okay, so good. So I can work modulo p, and I have a finite field FP. Now there's another just one more notion that I want to talk about. It's kind of the analog of so when I'm doing this integral, let me say sort of more generally, of x to the a 1 minus x to the b, I know what I'm going to do for the integral. I'm going to just sum over all the i's, from all the i's mod p. But what is the analog of these exponentials? And the analog of these exponentials are characters. Now, what is a character? What's the important aspect of an exponential? the important aspect of an exponential of this function is just that if I say that f of x is x to the a for some fixed a, then f of x, f of y is equal to f of xy. Okay, so I'd like to find something mod p that has exactly the same same properties, and this can happen. There's a variety of ways of talking about it. For example, let's say I'm working modulo 5. Okay. So let me take something like let me look at some element like 2, and let me look at powers of 2. So there's 2 squared, which is 4. There's 2 cubed, which is 3, and there's 2 to the 4th, which is 1, mod 5. Okay. So you notice that I chose nicely in this case. All the powers of 2 are distinct, mod 5. 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. It's guaranteed in general, this is Fermat's little theorem, it's guaranteed that a to the p minus 1 is always equal to 1 mod p. But we found something stronger here. We found an element, all of whose powers generates the entire field. Okay, so that's wonderful. That means that we understand everything else about the multiplicative properties of this field, because we can generate everything as the exponential of some elements. In fact, the number of these elements is given by the Euler quotient function of p minus 1, where the Euler quotient function of n is the number of integers less than n, which where the GCD of I and n is 1. So the quotient of actually a prime itself is p minus 1, but now we're talking about the quotient of p minus 1. Okay, so good. So let's say we have one of these guys. Then if we have one of these guys, then we can have an analog of this exponential function that we talked about. So what I can do, in other words, it tells me that there's a unique, so let's say a is one of these things, such that a squared, a cubed, up to a to the p minus 1 gives me all of 1, 2, up to p minus 1, mod p. If a is one of these guys, then the whole point is that there's a solution to a to the j is equal to b. There's a unique solution for j of b. Well, not quite unique because of the fact that everything here is order p minus 1. So I can take j of b and shift by j of b plus anything times p minus 1. But modulo p minus 1, not p, modulo p minus 1, it is unique. Okay, so let me define that. So it's then natural to define e to the 2 pi I over p minus 1 times this j of this. So I'm gonna define for any element mod p, any chi of I, I'm going to define this to be e to the 2 pi, bad notation, for any chi of, I don't know, z, I'm going to define, for any z, I'm going to define the chi of z to be e to the 2 pi I j of z over p minus 1. And you'll see this is unique. Of course, I have to pick my base. I choose this base. I choose the a, so that a to the j of z is equal to z. I make this choice. I'm choosing a. It implicitly depends on a. But having made this choice, I define this function. And now this function has the same multiplicative property that has exactly the properties that we need. So once you have these characters, then you can find finite field analogs of all the kind of integrals that we're talking about. And so, for instance, instead of talking about the integral dx, x to the a, 1 minus x to the b, you can talk about the sum over all i's, e to the 2 pi I, let me call this the sum over all the z's, like chi of z to the a, chi of 1 minus z to the b. That would be the analog. Okay. So, and you can do this for all the spaces that we're talking about. All the the stringy canonical forms, the cluster, string amplitudes, and so on. They all have natural number theoretic cousins. And literally this one is called a Jacobi sum. And there's a beautiful relationship between these objects and, you know, just like the beta function looks like gamma of A, gamma of B over gamma of A plus B. Well, the Jacobi sum, when you replace it by finite field, is actually a Gauss sum of A, a Gauss sum of B over a Gauss sum of A plus B. And there's lots of nice number theoretic properties of these guys. And I think it's a very natural question to ask whether there's something interesting about the finite field extension of in this sort of string amplitudes and of these more general, all the more general kind of integrals that we're running into in this business. The main obstruction to doing something here, I think it's sort of very interesting to explore. The main obstruction to doing something is it's not obvious what you're looking for. It's not obvious what the analog of a pole is in finite fields. And this is something that I've asked some, you know, famous number theorists about. Maybe I haven't asked the right famous number theorists, but there's all kinds of, you know, there's all sorts of analogies between number theory, of course, geometry, analysis, and so on. But this idea of the analog of a logarithmic singularity, is there a natural analog of a number theoretic singularity over finite fields? That's not, at least everyone that I've talked to has not found an immediate analog of that. But anyway, there are a very interesting set of objects that you can start exploring, and they have reason to have nice number theoretic properties, I think.
Thanks, Nima. I was hoping you would say something about counting points on curves.
Okay, right.
Maybe that's two or three.
I thought that's what you meant. Okay, so let me say something. Let me say something about that. All right. So this is okay. So let me tell. This is for amplitudes. This is for amplitudes aficionados. But let me tell you something interesting about Park-Taylor factors. And this is going to be the beginning of something that which will get to the direction of what Mark was talking about. So we know that we can talk about these Park-Taylor factors, like however you want to think about them. So d2 times n sigma over 1, 2 up to n1, however you want to think about them, oops. Oh, my pen is dying now. Weird. Sorry, guys. Hold on a sec. Let's see what I can do. Uh-oh.
Uh-oh.
Let's see. Let's see if I can switch to this one. It's not my pen. I think it's actually this whole.
Your mouse. Is it your mouse? Did we kill your mouse?
No, it's just 1 second. Let me see what I can do. Let's see. This is weird. Yeah, everything. Yeah, I'm not. One moment. One moment. Let's try this again. Okay, this seems to work now. Yeah, my other thing just seemed to. All right, let me share the screen again. Let's go here. Okay. Yeah. Okay, so let's say we had talked about the form dz1 through dzn mod SL2, the usual Park-Taylor factor, where z1 minus z2, the zn minus z1. Okay. And okay, we know that. So we know what is this? This is a sort of top form that we can have on this space where we have where the singularities can occur when the z's collide with each other. We also know, well, we know lots of things that this is just what we get in one ordering, but we know that we can have any ordering of the points. So we can have Park-Taylor factors in different orderings, and we know that there's lots of identities that are satisfied between these orderings. There's BCJ relations. There's the KK basis, BCJ relations, all sorts of things about the different orderings for even this top form. On top of that, there's questions you could ask that I certainly hadn't asked before and I didn't know how to answer. Like, let's say you don't care about a top form. Let's say you want some lower forms. You want to know how many lower forms are there, with the property that you just they only have singularities where the z's collide with each other. Okay, so there's so in other words, you want to know something about the cohomology of this space. How many forms? How many independent forms can you write that have the singularities just when the z's collide? Naively, this seems like a question where it's an analytic question. You write down a form, you write down the lower form, you see whether you can well, naively it seems like an analytic question anyway. But it turns out that there's an amazing way to answer this question, or at least begin to answer this question, which this is all completely standard stuff, but I just learned it from my friends, from Thomas Lamb especially, who explained it all beautifully to me. That there's a way to answer these questions about the cohomology of these spaces, and on top of that, learn about how many components there are, how many orderings, Euler characteristics, BCJ, all that kind of stuff, from an extremely simple, and it's also a strategy you can take if you don't understand some space, if you don't know the kind of forms you can write on it, if you don't know if it's going to just be d log forms, maybe there's something more complicated. If you're trying to understand what a space looks like, there's a few quick diagnostics that you can do that just involve counting points, where you think about the space as the space is defined not over the complex or the reals, but over f sub p. In the easiest case, over primes, over modular arithmetic mod p. And let me just illustrate how this works. Let me just illustrate how this works for this question of counting all the different kind of forms we can have on the space of endpoints on P1. Okay, so I want to illustrate. So again, the question that we want to ask is all the independent forms, or really the sort of the basis for the cohomology of endpoints on P1. And what we're going to do, we're going to get the answer to this question in the following way. We're just going to count how many points are there. How many points are there on this space? So if the space that we're talking about is V, we're going to just count the number of points mod P. I'll be specific about what we mean by this in a second. So let's just first illustrate this with the case of n equals 4. So what is the space that we're talking about? As usual, we set one thing to 0, the other one to 1, one is to infinity, so it's gone. So I have 0, 1, and z. Okay, and so what I want to do is, however, I want to avoid when z equals 0 and when z equals 1. So those are the things that I'm throwing out of the space. Okay, so that's where the singularities are. Those are the points that I'm throwing out of the space. And so now I want to know how many points are there. What are the number of points mod p where p is not equal to 0 or 1? Well, how many points are there? The answer is very simple. It's p minus 2 points. Okay. So if n equals 4, you notice something that's so trivial in this case, but it's already a little interesting that you remember that the finite fields only make sense mod p when p is prime. Nonetheless, when we do our counting, we get a formula that's just a polynomial in p. It's, in other words, the formula doesn't know that p is supposed to be prime. That is special. And when it happens that the number of points mod p is polynomial, there's something good happening about the space. And that polynomial has a lot of information about the cohomology that we're interested in. In order to see what's going on here, let's go a little bit higher. Let's go to n equals 5. So again, there's 0, 1, and then I have z1 and z2. And what do I have to do? None of these things can equal 0 or 1. None of 1 or 2 can equal 0 or 1. And I also can't z1 equal z2. So there are p minus 2 choices for the first guy, and p minus 3 choices. So there's p minus 2 choices for z1, p minus 3 choices for z2. Okay, so this is the number of points that I have mod p. Once again, you see that it's a polynomial in p. And okay, obviously in general, for general n, I have p minus 2, p minus 3, up to p minus n plus 2 is the number of points I have mod p. Okay. Now, let's look at this. Formula, and I'm going to do a. Let's look at it. Let's look at a couple of special values of it. Okay. Let's look at what happens when p equals 0. Okay. When p equals 0, so if we do this for if we do this for n equals 4, n equals 5, and so on. So here we have p minus 2, p minus 2, p minus 3, and so on, right? So when I put p equals 0, if I look at the modulus of this just this magnitude as p goes to 0, this is equal to 2, this is equal to 6, and so on. Okay. Now, those of you who know about the relations between part-Taylor factors will recognize these numbers. Okay, if I put p equals 2, 6, and so on, these are the number of elements in the KK basis, the Kleist-Keif basis for part-Taylor factors. In other words, these are the number of independent part-Taylor factors where you just have the ordinary partial fraction identities between them. They don't know anything about BCJ or anything like that. Okay, but that's the number that we get in this case. So this number is n minus 2 factorial. Okay, all right, that's an interesting number. Now let's look at what happens when. Let's look at what happens when. Let's look at what happens when p equals minus 1. Okay. So p equals minus 1. So that actually, before I do that, let's look at what happens when p equals plus 1. So when p equals plus 1, what do these numbers look like? Then for n equals 4, I have 1. For n equals 5, I have 2, and so on. When I have, in general, this is n minus 3 factorial. So this same polynomial evaluated at p equals minus 1 seems to give me the number of independent part-Taylor, the number of independent ordered amplitudes using the BCJ relations. And finally, if I put p equals -1, then what I get from these numbers is, let's say for n equals 4, n equals 5, and so on. N equals 4, I get 3. N equals 5, if I put p equals -1, I get 3 times 4, I get 12, and so on. So this is equal to n minus 1 factorial over 2. And this is exactly the number of orderings, just the number of different color orderings that we would be talking about. Right? So none of this is a coincidence. So let me explain how you read these off in this example. So the claim is that when n of p is polynomial, and then there is polynomial in p. And by the way, how do you decide if it's polynomial in p? In this simple example, we could just count very easily, and we could see that it's polynomial in p. But let's say you have some more complicated space you don't understand. What you do is you just do it on the computer. You just count. And you plot, and then you see if you can fit it. And that's already good enough. When you go to like prime into the 50s, that already gives you a lot of interesting information. But let me tell you what happens when n of p is polynomial in p. When it's polynomial in p, n of p really expands. For example, if I do the example n equals 5, it's p minus 2, p minus 3 is p squared minus 5p plus 6. And you really interpret this as exactly the dimension of the cohomology in every degree. 6 is the number of 2 forms. 5 is the number of 1 forms. And of course, 1 is the number of 0 forms. Okay, so this immediately, so when it's polynomial, without doing any work other than counting the number of solutions, mod p, you have determined something not only about the number of independent top forms, but all the forms of all degrees as you go down. The cohomology in all the degrees. And that also explains why when we put p equals +1, what we're doing is actually computing the Euler characteristic of this space. When we put p equals +1, we're taking the alternating sum of the dimensions of the cohomologies, and that's exactly the Euler characteristic. So the Euler characteristic of the space of n points on P1, taking out when any points coincide, is n minus 3 factorial. And there's actually a good reason why that's the same as the number of independent BCJ numerator. It has nothing to do with strings and monogamy relations and all that stuff. That n minus 3 factorial is just a very basic feature of this configuration space of n points on P1. When you put p equals 1, you get the Euler characteristic of the variety thought of as a complex space. And when you put p equals -1, you get the Euler characteristic of the variety thought of as a real space. So now what does that mean? When I put p equals -1, here we got n minus 1 factorial over 2. But what does this space look like as a real space? Well, when the points are literally real, the space just breaks up into a bunch of, into all the different orderings, and each one by itself is contractible. So the Euler characteristic just counts the total number of components, and that's why it tells us that the total number of components is actually equal, it gives us the right answer, and it tells us it's equal to n minus 1 factorial over 2. So this is, anyway, as I said, it's very well known to our math friends, but I was really blown away that all of this connection between the Bay conjectures and this amazing connection between the arithmetic, the properties and topological properties of these spaces and all this stuff is actually practical. That you can be struggling to try to understand some space, and then instead of struggling for a long time to see if you can find some forms and determine the sort of cohomology by hand, you can just do this count quickly to see if something good is happening. And the definition of something good, the best thing is if the point count is actually polynomial. The next best thing is if the point count is almost polynomial, which means that it's a different polynomial depending on like modular properties of P. For instance, you might get an answer, one answer of P is 1 mod 3 and a different answer of P is 2 mod 3. if that's the case, then essentially everything that I said is still true. You can still determine the cohomologies and so on in this way, and learn about the Euler characteristics, the number of regions, and so on. But there's a little bit more to the structure of the cohomology. There's some sort of torsion there's some torsion in the homology that knows about whether that's P is 1 mod 3 or 2 mod 3 and so on. The generic behavior is when it's not polynomial, and then other things happen. But it looks like all the spaces that we like that are associated with D-log forms and polylogs when we integrate and so on and so forth have these nice polynomial or quasi-polynomial point counts. And I encourage you to do the following exercise, just as an example of how this works. It's really cool. Actually, before doing this, just in ordinary loop momentum space, nothing fancy. In ordinary loop momentum space, just count. Let's say at n points, you can do it at 4 points too. But for more fun, at n points, look at a general loop diagram, a one loop diagram, L squared, L plus P1 squared, blah, blah, the usual thing, right? L minus Pn squared. And now just ask the question of the point count of the space where you throw out L squared equals 0, L plus P1 squared equals 0, and so on. When you do this, you have to make some generic choices for the P's, but it doesn't really matter what it is, okay? So do this point count and discover to your amazement that it's polynomial. And the fact that it's polynomial explains why when we do these integrals, we just get dilogues. If we do it in 4 dimensions, it's related to the D-logness of the answer and the polylogarithmicness of the answer. And after you do that, look at the famous sunrise diagram and just play with it on the computer, and you'll find if you put generic masses here and you do the same thing, you look at the variety where you throw out the place where these propagators go to 0. There's nothing polynomial about the behavior at all. But if you specialize in the cases where the masses are all equal and equal to the external mass, where, and by the way, when the masses are generic, we know that this answer is elliptic. But if you specialize in the case where the masses are all equal and equal to the external mass, where we know the answer degenerates to being polylogarithmic, you'll see that you'll recover a polynomial point count. Okay, so there's and I think that you know, certain kinds of amplitude integrator experts know all about this, but it's another direction that I think is really fascinating to try to understand something about the point counts for some of these fancier positive geometries that we're trying to understand. Okay.
Nima, quick question on this point. There's a hierarchy of these higher integrals, elliptic and then Calabi-Yau, so there's a whole
how is that reflected in the point counts?
Yeah.
It is reflected in some interesting way in the point counts that I don't understand. I don't understand in detail. Already in the elliptic case, you're supposed to ask different questions. Instead of doing the point count, you actually start looking at things that look like these Jacobi sums and so on instead. And there's something about the scaling. So once you start doing that, you're like averaging a lot of phases over this over the finite fields or over this variety. And so there should be a kind of a square root cancellation for averaging over a lot of these phases. But something about the sort of precise coefficient of that square root as you go to large P tells you something about some characteristic of the variety that you're talking about. You're supposed to get that's supposed to have some fingerprint of ellipticity or something else. But I don't. Thomas explained it all to me. When he explained it, I understood it, and it was really nice. I don't remember the details now. But anyway, you have to start asking this different question. Instead of just counting, you have to start doing something that looks like those Jacobi sum formulas and average over powers of these characters instead. And we should. This is something that I would make for a great journal club talk.
Can I ask you a question unrelated to this point?
Sure.
I understand that an unknown physics can show up as a lack of unitarity once I only consider the known physics. for example, imagine I don't know about Higgs and I find a massive SU2, or I don't know about the third generation of quarks and I found a CP violating phase. Is there anything that geometry can tell us about this new physics that can restore unitarity?
You mean like restore unitarity, like with WW scattering and the Higgs and things like that?
Yeah.
Well, I mean, I think there's a kind of uniform answer to these questions. You see, everything that we're talking about so far is just ordinary physics. We're not reformulating any. We're not doing any new physics at all. In fact, we're seeing all the structure in good old-fashioned gluons or even stupid phi-cube theory. So we're not talking about new physics beyond the Standard Model or anything like that. These questions have something to do with the kind of structure, some basic structure in quantum field theory, and not so much about this or that particle that might come beyond the Standard Model, which is extremely interesting and I've spent a lot of my life thinking about. But at the moment, these questions are not about that. Having said all of that, I think it's conceivable that this way of thinking about physics attached to geometry or generalizations. I mean, I'm not at all wedded to these particular set of ideas. It's just what we've seen so far. Maybe even much more interesting, much deeper ideas will likely come out as we explore these things more. I have no preconceptions about what will turn out to be important in this business. I just think it's better to do something than nothing. But I do think it's conceivable. There is one thing that we've seen here. And the one thing that we've seen is that we can have representations of totally ordinary physics that don't look like ordinary physics. They're not recognizable as local physics, as Feynman diagrams, or they're not recognizable as that. They're something else. And that something else, however, brings some hidden symmetry and hidden properties to light. And exactly those properties are made invisible when we insist to write the answer in terms of Feynman diagrams. So that's a sort of a general thing that we've seen. And that general theme might have something to do. It's very speculative, but it might have something to do with solutions to difficult problems like the hierarchy and the cosmological constant problem. It's a super long shot, but I've spent some time sort of thinking about this and speculating about it. Back on Wednesday at the Pheno conference, I gave a talk where I talked about some of the speculations that were literally motivated by this. In fact, I said that what motivates these speculations are all this work in amplitudes that has this flavor of giving us representations of physical objects in a way that don't look familiar. But when you insist on writing them in terms of things that look familiar, you obscure these hidden symmetries. And I gave some toy examples in that talk. If you want to, I think it's probably online if you want to look on, and actually it involves some interesting number theoretic aspects as well. That are familiar to us from thinking about polylogarithms and things like that in amplitudes for how that might work. Actually, since you brought it up, and maybe I'll say this as a last sort of interesting recreational thing. Let me give you an idea of what I have in mind. This is actually what I mentioned in that talk. This is the sort of fantasy. The sort of fantasy is that the fantasy is that just like as we've seen that amplitudes are somehow some integrals over some funny abstract space of some funny form, and this thing does not obviously look like Feynman diagrams, but there's some way of writing it that looks like Feynman diagrams. But this makes some hidden symmetries manifest. But insisting on writing as Feynman diagrams obscures the asymmetry. Okay? So could it be that there's some kind of formula for the potential of the Higgs or the cosmological constant that also looks like an integral over some funny abstract space of some funny form, and that in this form it's manifestly tiny? However, the insistence on writing it, however, there's a way of writing it so that it looks like a field theory calculation, but when it looks like a field theory calculation, it looks fine-tuned. So that's at least a sort of strategy, and it's a strategy that is that's inspired by these kind of things we've seen in amplitudes. And I want to give you a toy example of this phenomenon. And I'll bring it up because it's actually related to some very basic things that we talk about all the time in the amplitudes business anyway. So, so here's the.
Sorry, can I ask you a question right now?
Yeah.
So about the Higgs potential itself, my understanding is that having the massive massive SU2 somehow gives this specified at least the order of magnitude of the mass of the Higgs. Otherwise, it won't restore unitarity. By fine-tuning, you mean something like that, or something?
Oh, no. I'm talking about the story of the fine-tuning associated with the hierarchy problem. What you're talking about is not the Higgs mass itself. What you're talking about is the ratio of the Higgs mass squared to the W mass squared. Okay, so that ratio could not be too big. This ratio could not be too big without having unitarity problems and so on. Given that we saw the W at 80 GeV, the W and the Z at 80 and 90 GeV, M Higgs had to be smaller than around 4 pi times the scale of the W and the Z masses, really more precisely 4 pi over G times W and Z, in order to not have problems with the unitarity. And of course, it came in much earlier than that, okay? But that's really about this ratio. It's not about the absolute scale of the Higgs mass itself. The difficulty with the hierarchy problem is that we don't understand why the absolute scale of the Higgs mass, and therefore of the W mass and everything else, is so much lower than ultraviolet scales like the Planck scale. And so here I want to give a sort of toy example of that illustrates that it's possible to have some quantity that's obviously tiny, exponentially tiny, but that it's necessarily built out of two different parts, out of a part that is rational and a part that's transcendental, such that the sum is guaranteed to have a huge cancellation between the two pieces. And this, I think, is a toy example that you could hope along the lines of the fantasy that I just talked about to flesh into a new understanding of the hierarchy or the cosmological concept problem. But let me just tell you how it works, because it's a very cool little story, and it'll also give you a simple way to impress your friends. Well, anyway, you'll see what they should be impressed with in a second. So let's start with something really simple, like log 2. Log 2 is the integral 0 to 1 dx over 1 plus x. And you can ask, why do we get something as fancy as log 2 out of this integral? After all, if I put squares there, I'd just get a rational number. If it was a positive power, I'd get a rational number. Why do I get this sort of a transcendental number? And it's precisely because what I have here has a simple pole. It has a logarithmic singularity. So, you know, literally the star of a lot of our show earlier today, okay? It's literally because this has a log singularity at x equals minus 1. And because of that singularity, you know, even though I'm doing the integral from 0 to 1, I could have done it on a different contour that enclosed this pole, and then the answer would have differed by 2 pi I. So that's why this is as fancy as log 2. But that immediately tells you something cool. That immediately tells you that, let me look at the following integral. Let's look at, and actually this is all quite beautifully explained in a talk that Francis Brown gave at the Institute. You can find it on the Institute website. So let's say you have this integral 0 to 1 dx over 1 plus x. But now I'm going to put a factor here that looks like x times 1 minus x over 1 plus x, say, to the n. All right? Now, sorry, I'm going to do a slightly different.
Nima, do you need to use Mathematica? Like you have that one, right?
Yeah, I mean, I can. Yeah, let me. But before getting to Mathematica, I'll use it. But I first want to just illustrate a little point here. Oops. Yeah. So let me do a slightly different example of the one that Francis likes. I'll illustrate two different points. So I'm going to put, well, actually, before saying even what, let me say a general point. Let's say you have this dx over x, dx over 1 plus x, and you put some polynomial in x here. then it's guaranteed ahead of time, it's guaranteed that this looks like P of -1, where the residue is, times log 2, and that everything else will be rational. Okay, and that's again for the simple reason, the only reason this has a log 2 in it is the residue at x equals -1. If there is no residue at x equals -1, the rest would be rational. So you know for a fact ahead of time that this looks like P at -1 log 2 times something rational. So now let me pick an example. Let me pick an example that P of x is x times 1 minus x over 2. You'll notice that P of -1 is equal to -1, so it's plus or minus 1. So this integral dx over 1 plus x, and let me say I take this to a power of n, so this is -1 to the n. This is x1 minus x over 2 to the n. This is plus minus 1 plus minus log 2 plus something rational. But on the other hand, you also see this is minuscule. It's minuscule because x1 minus x over 2 is smaller than 1 over 8 to the n, between 0 and 1. And so you see that I have an integral that it begins life as something that's obviously exponentially tiny, but for very good number theoretic reasons, even simpler than that, it must be expressed as the sum of two qualitatively different pieces that are both large, and they have to cancel to high accuracy. Okay? So let me show you how this works. Let's just see how it works on Mathematica. You could all do it yourselves, even more quickly than me. But let's just see how it works. Can you see? Let's see. Can you see? No, you can't see.
Oh, you need to cancel your screen share and then restart your screen share.
Sure. Let me do that. Okay. New share. Okay. Oh, here. Okay. All right. Oops. All right. So. Okay, so let's look at what this looks like. Let's look at the as promised, integrate x 1 over 1 plus x. Let's do x 1 minus x over 2.
Not showing up, Nima.
Oh, sorry about that. Just one moment. There we go. Is that showing up now? Okay, good. All right. So let's say we do this integral 1 over 1 plus x 1 minus x over 2, let's say to the 5th. From x goes from 0 to 1. Okay, so you see, as promised, you get something log 2 plus something rational, and if we numerically evaluate it, it's exponentially small. It's very small, right? So if I put to the 10th here, it takes it longer, and it's obviously exponentially small. That was clear. So you see, if no one told you where this came from, you'd be like, wow, it's amazing that I have two numbers, order 1, that cancel to incredibly high accuracy, but there's a very good reason. There's a mechanism why it happens, and we've explained it. Actually, this little curiosity happens in quantum field theory. If you taken a field theory course and done some real physics in the field theory course, like in Peskin and Schroeder, you'll, for example, see there's a formula for the lifetime of positronia. And okay, there's a lot of factors in the formula, but there's a funny factor in front of the whole thing, which is pi squared minus 9. Pi squared minus 9 is a little bit small. There's a little bit of a cancellation. Not a very huge one, but still. You might wonder if it's just a curiosity, if it's an accident. It's not an accident. It's exactly the same mechanism. That pi squared minus 9 is actually coming from a phase space integral. The phase space integral is manifestly small, but for exactly the same reason. It's built out of the sum of two pieces, one that's rational and one that's transcendental, that are forced to cancel against each other to high accuracy. Let me give you a more fun example for pi. So to get pi, I have to get a residue at x equals, I have to get log I. So I have to have a residue at, I have to have a factor of 1 over 1 plus x squared. And actually, if you just do this, just what we did before, let's just do 1 power here. Then if you integrate, you see you get both pi as well as log 2. But if you put this squared, you just get log 2. If you put it cubed, you get a linear combination of pi, again, of pi and log 2. But if you make it to the 4th power, and in fact, for any multiple of 4, look at what cool thing happens. What you get is pi minus 22 over 7. That's why pi minus 22 over 7 is such a good approximation to pi. It's for exactly the same mechanism. And you know, pi minus 22 over 7 really is a really good approximation, right? It's valid to 1 part in 1,000, despite the fact that there's only 2 digits in the 22, right? But this happens for exactly the same reason. Now, if you look at Francis's talk, and you can play with it yourself, you can actually use these methods with a little variation on what we're talking about here. In fact, instead of doing x1 minus x over 2, it's important for detailed reasons to put 1 over 1 plus x there instead. For the purpose that I was just talking about, it doesn't make any difference, but anyway, you can use these methods to actually prove that log 2 is irrational, that pi is irrational, and in fact, the whole idea of finding incredibly good rational approximations to irrational numbers is the classical way, going back to 1800s, that you can prove that numbers are irrational. So this is a very well-known phenomenon. In amplitudes, we talk all the time about transcendentality and the polylogarithm and so on. And of course, the famous thing that you'll learn from Sasha Goncharov or Mark and Nastia is that we don't even know that numbers like zeta of 5, for example, we don't even know if they're irrational, never mind that they're transcendental. But there was an amazing breakthrough in the late 1970s made by Apéry, who proved that zeta of 3 is irrational. And then a lot of this business about symbology and so on, and cousins, is about finding linear relations between these different zeta values, so that you can prove that some number of them are that many of them are irrational, or various linear combinations can't all be rational, and so on. And what you'll see in that talk of Francis Brown is a more conceptual understanding for where these things come from. And they're all the same mechanism of trying to find integrals that are manifestly minuscule, but where when you express them for good reasons, their number theoretic content only spits out like zeta of 3, rather than just zeta of 3 plus zeta of 2 or something like that. Zeta of 3 plus pi times zeta of 2, that would pollute it with a zeta of 2. The kind of magic is to find the right integrals that just spit out the zeta values that you want. And the really remarkable thing is that the kind of integrals you get are exactly string integrals, exactly the kind of string integrals that we've been talking about, except that what you do, instead of regulating the integrals by putting these alpha prime, these powers of alpha prime to the s, you do something simpler. You imagine that you do the integral of a part Taylor factor over one region, which has no singularities at all on another region. You can begin to do this already starting at 5 points. At 5 points, there are the 2 orderings, 1, 2, 3, 4, 5, and I forget, 1, 3, 5, 2, 4. Those 2 orderings don't have any poles in common. And so you can do just an integrative, an integral of the flat-out canonical form of D2n with one ordering, but you can integrate it over the positive region of another ordering. And if you do those integrals and then also weight them with analogs of these powers, of the power of these factors, then you exactly get these amazing rational approximations to zeta values, which are the origin of the deeper conceptual origin for the irrationality proofs for zeta of 3 and so on. So anyway, I recommend that you look at Francis's talk. It's a really beautiful subject. But I was asked in the beginning whether there might be some way this would tell us about new physics, and this is super speculative. So I said before, we're allowed to fantasize after 10. This is what we're allowed to do after 11. But if I had to dream, and I think it's a real long shot, but still, we have seen that it's possible to represent physical observables in a way that does not look like obvious physics, and that doing that brings out hidden structures, and that conversely, writing it as standard physics hides those symmetries and those miraculous facts. Maybe something like that is going on with the Higgs mass and the cosmological constant, and these are kind of toy examples for what it might look like.
Thank you so much. This toy model was so magically interesting. Thank you.
Yeah, you'll really enjoy that. You'll really enjoy that talk by Francis's. I really encourage you to look at that.
Nima, thanks. That's great. Another direction in which you could have taken the question about, if I recall, the original phrasing of the question was about the geometrization of unitarity. You could have taken that in the direction of the bootstrap and told us about the, I mean, far be it for me to want to prolong things artificially, but maybe, you know, you could have presented the shortest proof of the critical dimension of string theory.
Oh, well, actually, funny you should ask. Funny you should ask. So one of our postdocs at the Institute is really has made some. I mean, it's not totally solved that problem that Yutin and I have been obsessed with it for a long time, but has some really new, great ideas about it, which are really interesting. But anyway, let me. Okay, so I think this is what Mark wants me to tell you guys about, and I'll be delighted to do it. Yeah, this is all super cool. So just a second. Just a second. Let me see if I can go back to this other. Okay. Okay. So I think, but actually, in order to take this out of something purely recreational, let me say something about string amplitudes in general. So I have a prejudice, I could be wrong, but I very strongly feel that there should be some way of thinking about
we don't see a screen yet.
Oh, sorry.
Or the wrong screen, maybe.
Sorry, let me do this. Let me do this. Yeah, okay, here we go. So I very strongly feel that just like we've seen over the last, 10 years, just like we've seen that it's possible to think about gauge theory amplitudes, gravity amplitudes, and so on without a Lagrangian, without gauge redundancy, and so on and so forth. And that doing that brings all this wonderful structure to light. It's really strange that string perturbation theory, now string theory should be the greatest S-matrix theory of all time, right? That's where it was born. That's the most magical amplitude, the most magical thing at the level. String theory in flat space is maybe the most magical thing in theoretical physics has ever seen. It's not obvious it's correct or true or relevant to the real world in all details, but as far as just pure magic goes, it's sort of hard to imagine something that with a bigger shock value when you see how it works. But it's weird that its perturbation theory sucks so much. And I think one aspect is that if you think that this sort of fealty to gauge redundancy, if you think that this fealty to gauge redundancy is a bad thing in our understanding of gluon and graviton amplitudes, then string theory's attitude to gauge redundancy is, I love gauge redundancy. Give me more. There's even more gauge redundancy on the world sheet. All the gauge symmetries we know of are even lifted to something that depends on this extra signal parameter of the world sheet. So at least morally, it seems like if you believe that that getting rid of that redundancy did something good in gauge theory and gravity, then there should also be a way of thinking about string amplitudes which doesn't have the world sheet in it. The world sheet is not such a star. Now, we've seen in the talk today, in our talks today earlier, we've seen some little concrete examples of this. After all, we managed to go directly from kinematical space and then ask these sort of different questions. Nowhere did we see a world sheet conformal field theory. Nowhere did we see, well, anything that looked like a world sheet. And we got directly to the Kobe-Nielsen formula. Of course, it's only at tree level, only for this sort of toy model and so on, but that's at least some indication that there should be some way of thinking about string amplitudes of the world sheet is not such a necessity. It kind of, again, it comes out as an interpretation, but the fact that you can interpret as the world sheet is a big output of this whole way of thinking about things that we talked about and not an input. So So anyway, it's a prejudice, but I strongly think that there should be some way of thinking about string theory without the worldsheet. And the little thing that I'm about to show you is just one example of this. Okay, so but again, if you want to see magic, this is really magic par excellence. So let's begin by looking at open string scattering amplitudes. And here there's this formula. I'll just write it down if you haven't seen it. That's what it is. Now there's dependence on polarizations and so on and so forth out in front. But let me just imagine that I extract some scalar component, and that will multiply this whole thing by a factor of s squared. Okay, so that's what the amplitude looks like. Okay, so that's a sort of famous Veneziano-like amplitude, except now it's for massless particles, so massless scalars. Okay, and now here, and this is one of the really magical things about string theory. If someone gives you some amplitude, and this is a tree amplitude, it's, you know, you can't just check that it's soft at infinity and everything is fine, it looks good. You have to check that when you have a pole like s goes to m squared, you have to be able to interpret this pole as the exchange of particles of spin f with various spins j, let's say, with some positive probabilities. And what that means, in textbooks we learned about the partial wave expansion. So it means that if I look at the amplitude as s goes to m squared, so it looks like 1 over s minus m squared times some polynomial in the scattering angle, cosine theta. You know, so 2 are in and 2 are out, there's a polynomial in theta. But the crucial thing is that this polynomial in cosine theta has to be expressible as a sum over Legendre polynomials, pj of cosine theta, with positive coefficients. I'll call them little pj. And these positive coefficients are interpreted as the probability for, this is the probability for producing a particle of spin j. Now, Legendre polynomials are the orthogonal polynomials on the sphere in 3 dimensions. If I was in 2 dimensions, there would be cosines. If I was in higher dimensions, in general, they're called Gegenbauer polynomials. Okay, but in any case, this is a major constraint, that we have to be able to expand the residue as at s goes to m squared into a sum of a Legendre polynomial with positive coefficients. That's the magic, that it's positive coefficients. So let's see what the residues look like in this formula. So it's s squared gamma of minus s, gamma of minus t, over gamma of 1 minus s minus t. And let's see what happens as s goes to 0. Well, I put an s squared there, so the residue just vanished. By the way, as alpha prime goes to 0, I didn't put the alpha primes here. This goes like s squared times like 1 over st. Okay, so this is like s over t, which is what you'd expect from amplitude involving gluons. Okay, so s goes to 0, the residue is 0. As s goes to 1, the residue is 1. You can trivially see. As s goes to 2, the residue is 1 plus t. See, if s equals 2 here, I get a ratio of the gamma functions, and I get 1 plus t. Finally, when s goes to 3, the residue is 1 plus t times 2 plus t, and so on. So we get the higher and higher versions of these formulas. Okay, but I'm going to restrict myself to looking here at this example of s equals 3 because something wonderful happens there. So I want to write this. So I set s to 3. The residue looks like 1 plus t, 2 plus t, but I want to write this as a function of cosine theta. For this, we have to remember that for massless particles, t is equal to s halves times cosine theta minus 1. So here, s is equal to 3 in string units. So t is equal to 3 halves times cosine theta minus 1. And therefore, 1 plus t is 3 halves cos theta minus a half. And 2 plus t is 3 halves cos theta plus a half. And therefore, this residue, which is 1 plus t, 2 plus t, is 3 halves cos theta minus a half, 3 halves cos theta plus a half, which is 9/4 times cos squared theta minus a ninth. Now, that's great. The fact that there's a cosquared theta here means that we have a spin 2 particle. And in fact, in d spatial dimensions, the analog of the Legendre polynomial for spin 2, called the Gegenbauer polynomial again, in d, this looks like cosquared theta minus 1 over d. There's a dependence on the number of spatial dimensions because you have to take out the traces. And so that's fine. The coefficient of cosquared theta is positive, so I have a spin 2 particle with positive coefficient. That's fine. But notice that cosquared theta minus a ninth is cosquared theta minus 1 over d plus 1 over d minus 1 over 9. So while it's true that I have a spin 2 particle with positive probability, I also have a spin 0 particle. This is just multiplied by constant. But if the number of spatial dimensions is bigger than 9, this coefficient is negative. So I learned, amazingly, that this formula for the string amplitudes is not consistent. It violates unitarity unless the number of spatial dimensions is less than or equal to 9, or the number of space-time dimensions is less than or equal to 10. So we see the fact that string theory only makes sense in 10 dimensions, the superstring theory makes sense only in 10 dimensions, is sitting there in the heart of the actual amplitude. The amplitude tells you that it's not consistent if the number of dimensions is larger than, if the number of dimensions is larger than 10. We can repeat that exercise for the Veneziano amplitude and get the 25, or the 26 for the number of space-time dimensions. Okay, so that's quite beautiful. But here's the amazing thing. As you check whether this is true at higher and higher levels, it's an incredibly simple statement about a certain polynomial. Okay, so in fact, you can work out the residue of the polynomial for the open string, and the residue, now written as a function of cosine theta equals x. This is just an incredibly simple polynomial. It's the product of x minus n minus 2i over n at level n from I equals 1 to n minus 1. Okay, so you can think of this as just something that has evenly spaced roots all the way from almost to 1 and minus 1, but it's missing these ones, but it has the rest of these roots. Okay, and they're all evenly spaced, and it goes all the way up to n minus 2 over n. So the claim is that this polynomial, this polynomial Rn of x can be expanded. For example, it can be expanded as a sum over Gegenbauer polynomials of x with positive coefficients. And this is what it takes for the physical consistency of string theory. And of course, there's a proof in string theory, but the proof involves it's not a trivial proof. It's the no-ghost theorem. And it's, in the end, kind of indirect to prove such an incredibly simple statement. So there's some ridiculously simple statement about this polynomial that takes 100 pages of a string theory textbook to prove. That's kind of crucially tied to the physical consistency of the theory. So anyway, so this is, I think, yet another indication that trying to make these facts transparent and obvious is not obvious. And I think this is one of many indications to me that there should be some sort of deeply better way of thinking about string amplitudes. Anyway, but just for the simplest reason of all, for the greatest S-matrix theory of all time, it has a horrible, complicated, ugly perturbation theory, and it's hard to believe that that all this magic shows up for gluon and graviton scattering amplitudes and doesn't sort of extend to the full string amplitude. So thanks, Mark. Thanks for thanks for getting me to talk about that.
Yeah, that's great. Thanks, Nima. Any other questions? There was a question from the audience from someone whose anonymity I'll preserve, curious about tips for finding shark teeth.
Oh, well, actually, you're lucky because the relevant states are now reopening beaches and things like that. So yeah.
Awesome.
This is really a great thing. One thing. There's a number of places on the East Coast where you can do this. There's places in Maryland, South Carolina, Florida, North Carolina as well. And if you just Google, shark tooth hunting Maryland, there's a site called The Fossil Guy, and then that has a lot of links. And there's a little community of people who likes doing this. But anyway, you have to get good at doing it. So it takes a little while to get good at doing it. It's wonderful. It's a lot like physics. It's not trivial. You have to practice, but when it works, something totally magical happens. You go to the beach at low tide. You just walk back and forth on the water's edge, and you look to see that glint of this of the tooth, and mostly it doesn't work. But every now and then you see one, and time stops. You go, you grab it, you come look at it, and you hold something in your hand that's been in a shark's mouth 30 million years ago. It's completely, totally amazing. Whether it's small or big or whatever it is, doesn't matter. They're all amazing because they all came from a shark's mouth 30 million years ago. But anyway, there's a number of places on the East Coast. There's the sort of Calvert Cliffs area in Maryland. There's places in around Venice, in Venice Beach in Florida. A number of sort of rivers in the Carolinas. The Topsail Beach in North Carolina. And anyway, you have to go at low tide, and yeah, you go at low tide, and you just at these places where they're there in abundance, and you just walk on where the ocean meets the shore, and you look for them. And when I first got into it, I looked at I found a YouTube video by some sort of 12-year-old kid who was really good at it, and he was also a kind of a bratty kid. So he made this video of himself finding the teeth, and then but he was all like, "Oh, I had a bad day. I only found 40 teeth," and he was all being sort of humble bragging about it. But anyway, it was inspiring enough that I went to the beach that he went to, and we went there and looked for hours and hours and didn't find anything. So just nothing. Actually, I think that maybe the first day at the very end found one really, really tiny one, but it was really frustrating. So I briefly contemplated, because he had actually left his contact information. I briefly contemplated emailing him an email along the lines of, "Dear little boy, can we please meet on the beach so you can teach me?" And then I just, no, this can only go south. Why don't you come teach me how to do things? Will be our little secret. No, so I decided against it. And instead just kept going back, and after a while you get your eyes for it, and yeah, it's absolutely amazing fun. If you really become crazily hooked on it, then you can do things like there's a fossil festival in a little town in North Carolina where there's a mine, and every year they just dig out big piles of dirt and they pour them out. And those piles of dirt that they dig out from the mines are really fossil rich. So you go like the 50 crazy people who are crazy about these things, and you spend a day in the brutal sun combing through this hot pile, but you end up finding incredible teeth when you do it. If anyone is really serious about it and they want to actually do it, and you're in the Washington D.C. or Maryland area, and you really want to do it, you can shoot me an email, and I can take you to some of the fossil-rich areas and show you how it's done.
While maintaining social distance, of course.
While maintaining social distancing, I guess that's going to be problematic for a while. But
Nima, thanks. We have a lurking cosmologist in the audience who, if you don't find this is too off topic, is curious to hear if you have any thoughts on the Hubble tension.
Well, yeah. I mean, every attempt, every new physics attempt I could think of explaining it, like most people who thought about it, suck. So it's a very, very weird problem. It's really a, it's now I know Adam Rees very well. I mean, he's a tremendous physicist, and he's an amazing guy. And he, he was very bullish on it. And he kept telling me that it felt a lot like what happened with the accelerating universe before his discovery of the accelerating universe. But unlike the accelerating universe that had a one sentence explanation that anyone knew, the cosmological constant was utterly trivial and people didn't like it, but it was a beautiful explanation, no problem. Here, the phenomenology is really weird because what you need is something that modifies the expansion rate of the expansion rate of the universe right around the time of right around the time of recombination. You want to modify the expansion rate right around the time of recombination by maybe 5%. But the problem is that we know a lot about what the expansion rate looks like in the factor of 10 before that by the location of the peaks in the CMB power spectrum. When the universe became matter dominated, these perturbations came in and they started oscillating. So these famous acoustic oscillations, and those oscillations have been measured to great accuracy. So you can't mess with the expansion rate by more than few parts per mil in the decade before recombination. And then after recombination, in the late universe, we know a lot about the expansion history then. So what you need is some weirdo kind of new energy that is subdominant at a few per mil level, right around recombination. When the universe becomes transparent, it goes up to about 5%, and then it redshifts away even more quickly than radiation after that. And that's such a crazy combination of things to do that all the models look kind of crazy to me. So my feeling, without any real expertise, is that this will eventually go away. It'll be some combination of statistics and systematics and things that people don't understand. But anyway, I've done what I know how to do, which is to think about models that might explain it, and they're all terrible.
Nima, your voice is starting to show.
It is actually. It is. Yes, I'm getting old. Yeah. So.
Well, no, maybe it's been too long since we've let you had a drink. So.
Oh, fair enough. Yeah.
So maybe we should have pity on Nima at this stage, unless someone can think of a topic for his next lecture. How about you, Yaroslav? You know how to push Nima's buttons.
Oh, is Zara up? No way, Zara up here.
Well, he's connected to the call. That doesn't mean necessarily.
Yeah. Well, I'm here, but.
Look at that! Look at that! All right.
I'm looking for a person a few time zones to the west to sort of take over.
Yeah, it's still early here, kind of.
I know.
But I guess this was already longer than your marathon at Davis, so you can be satisfied.
Really? Is it? Oh, I guess the purely amplitudes part is. I guess it's true. It's true. Yeah. And there we have lunch breaks and things like that. So yeah, Davis was for sissies, Zira. That's kind of
Yeah, you should come again. Yeah.
It's California. Everyone's so relaxed. It's not. Yeah. Right. All right. Okay, guys. In that case, maybe I will go save my voice here because I have to speak next week as well. Although
then we should all give you a huge round of applause.
Thank you so much, Nima. This was great. Thank you.
Thank you. Thanks a lot, guys.
Thank you, Nima.
All right. Bye-bye.
Stay safe.
Yeah.
We'll upload the videos as soon as we can.
Yeah, right. Good luck. Thanks again. All right. Bye-bye, guys.
Good night.
Thank you so much.
No, my pleasure. Bye.